Participant joined in. Good morning, everyone. You cannot escape the responsibility of tomorrow by evading it today. Interesting quote by 16th US President Abraham Lincoln. I sincerely welcome all the participants who has been in the journey of 1 week online FDP program sponsored by AICTE Training and Learning on data science and artificial intelligence in chemical engineering recent trends and future outlook, organized by MVJ College of Engineering Department of Chemical Engineering. Today, we are in the third day of 7th session. Few lines about AI. Artificial intelligence makes it possible for machines to learn from experience, adjust to new inputs, and perform human-like tasks. Using technologies, computers can be trained to accomplish specific tasks by processing large amount of data and recognizing a pattern in the data. On this beautiful morning, we have a resource expert, Mr. Sanjay Venugopal, Senior Technologist of Yokogawa IA Technologies, Bangalore. Sir has a 25 years of industrial experience in the field of advanced process control, project execution, and technology development. The Sir has also worked in Honeywell and Aspen Tech, leading advanced process control technology suppliers for refineries and petrochemicals. His unique nature of revealing the industrial experience to academic personalities made him to stand among us today. With a short note, I would like to invite Mr. Sanjay Venugopal sir to deliver his speech on data analytic techniques deployed in chemical process industries for advanced control and optimization since the 90s. We welcome you to FDP platform, sir.
Thank you very much, Professor. Good morning to one and all. Before we start, let us double check the audio is okay for all of you.
It's okay, sir.
How about the display? I'm sharing the presentation now.
Yes, even the PPT is visible, sir.
Okay, fine. Thank you.
Thank you,
So,
sir.
thanks for giving this opportunity. In fact, I have been visiting MBJ in the last few years. In fact, we used to conduct face-to-face workshops on process control, advanced process control for the final year chemical engineering students. Unfortunately, due to COVID, this did not happen last year. But it's good that technology is coming to our help, and we are today discussing about this great topic. So I'm a chemical engineer, and I have been working in the field of process control. And process control has a lot of applications. Basically, chemical engineering has been using data since last 50 years, and especially process control is a big field wherein data analytics, data analysis, statistical process control. These are all very, very established techniques. So let us revisit these concepts which have been beneficial to continuous process industries, how these techniques are used. Okay, each technology has its benefits, advantages. At the same time, the technology has limitations also. So these limitations are what will trigger the new research, and there is a trigger point for the new artificial intelligence, machine learning, data analytics. There are different names, big data analysis. So we would like to understand the journey which started in early 80s or 90s and where we are today, and what are the open problems to be solved as far as industry is concerned. See, there are two parts to this. There is a research component and there is an industry component. When I say industry, these applications have to be taken to the shop floor. They have to run on day-to-day basis. There are some operators, field operators or control room operators who are the normal users of this technology. So you would see a gap that would exist between the research. When I say research, it is both academic research as well as industrial research. Academic research is way ahead in this area, but there are a lot of practical challenges to take these solutions to the shop floor. So most of the topics what I would explain today are not new for you academicians. I would only try to connect you how they are deployed, how they are used on a day-to-day basis in a factory like a refinery. Okay, so with that, I would get started. So I will try to give about 45 minutes for the explanation of the background and about 15 to 20 minutes for a demo. I would like to demonstrate using the industrial software, and as far as possible, try to raise your questions because that will be like a feedback for me, like how I'm going with my explanation. If there's any disconnect, please raise your hand and feel free to ask the questions. Okay, with that, we will get started. So these are the topics in this order that we would discuss about the importance of process control in a continuous process plant like a oil refinery or a petrochemical or a fertilizer industry. And typically the control systems, industrial control systems, which use regulatory control, that means your PID is the workhorse. What are the functions that PID do, and what are the limitations? That would lead to model predictive control. So this is the topic for the day, model predictive control. And what is this model? How it is constructed and how it is used for control. So we'll try to understand. So the start point, as it is obvious now for you, is the data. And this data is coming from plant. And this plant is a continuous plant. In addition to control, it is also important to measure the qualities. For quality, I mean the product qualities. It could be petrol, it could be diesel, it could be a polymer, etc., etc. And quality measurement is quite complex than temperature, pressure, flow level measurements. And we have some special technology called soft sensors. Okay, so this soft sensors together with the model predictive control is what is giving a good benefit. Benefit means in terms of monetary benefits. See, in industry, every single dollar to be spent. So people would look at what is the gain, okay, and how fast I would get back this investment. So end of the day, it's all economics. It is all business driven. So this technology is helping this continuous process industry to make more money. End of the day, that is all industry is all about. But there are conditions. It is not just making money. You know, a lot of conditions have to be met all the time, around the clock. So how these technologies help to ensure safety, to ensure quality, to ensure zero pollution, to ensure operator safety, etc., etc. Then we will look into a demo for a better understanding after going through some of the concepts. Then we will return to the control analysis because you are running this model predictive control day in, day out. And expectation is it has to do a lot of job, a lot of activities, and always give more money to plant people. So is it doing the job, the right job? So again, we come back to data analytics. Then we will visit one challenge area, I would say, as far as the industry is concerned. The nonlinear dynamics of a process and how to identify. If you look at the research, especially academic research, this is very evolved, matured also, but a lot of challenges which I would explain. And this is a trigger point for this new age of data analytics. You call it AI/ML, big data analysis. So we will have a following session from my colleague, Sri Sandeep Padiga, on Saturday. He would explain how this new technology is applied to this nonlinear model identification. So that is the connect point. We also have prepared some questions, MCQs, that is part of your procedures. So after this lecture, if you go through this lecture, I'm sure you will be able to understand this context of these questions. So let's move. What is process control? You all know this. I just want to recap from an industrial perspective. First and foremost, personnel and plant equipment safety. So safety is paramount, and process control equipments, process control logics, process control schemes play a very important role in this aspect. Any operator, plant operator, wants to maximize production, to maximize profits. So the product has to be on quality within the specifications. That is the key point for sales of the product. And most of these industries, as you know, they are highly energy intensive. In the sense, there's a lot of steam that is used to heat up the processes, and there is a lot of cooling, either cooling water or coolants, which are used for cooling down the processes. Or there's a lot of fuel gas or fuel oil burnt to keep running the furnaces. So in this age of fossil fuels going down and also increase of pollution, so how do we attack this problem of energy efficiency and also maintain the regulatory norms, because burning fossil fuels will carbon, that's a known fact. Yes, zero emissions. So most of the factories are now on zero emissions, and they're expected to display their all the pollution parameters at real time on the clock. So you see the list of expectations from process control. So it's quite demanding, and it has to be on job. Okay, so can this process control system do all this? So we'll try to understand using a plant problem. So this is a very well-known process. You have done a lot of analysis, understanding, designs around this. This is a simple distillation column. Call it a two-cut splitter because you have top and bottom streams. And the feed before introducing to the distillation column is heated to a furnace, multi-pass furnace. And once the feed enters, there's a flash vaporization. Low boiling vapors go up, and the high boiling liquid, they go down. This is mass transfer. It's a continuous exchange of cooling and heating, cooling at the top and heating at the bottom to ensure the volatiles are stripped off and the heaviers are pulled down to the bottom. So this is a continuous exchange of heat. There is an energy balance, there is a heat balance, mass balance. And of course, pressure of this column is very important to be monitored and controlled. So pressure control is very important for maintaining product quality. Pressure and temperature are twins, we know that. And this pressure and temperature column conditions will impact the quality of the top and bottom product. So this is the plant. So what is most important, as it is obvious, you want to increase the production and you want to maintain the top and bottom quality. You want to minimize the steam that is given to the reboiler. So you put all these conditions. Then, okay, I can do that, but what are my handles? What do I adjust to maintain all these so many conditions that you're demanding? Of course, if you are the operator, if you're given this top temperature, it is cascaded with the reflux. So you would adjust the top temperature set point. And also you would adjust the bottom temperature set point, which is cascaded with the reboil. So you have two handles. Okay. You have two handles, top temperature, bottom temperature, but you have to maintain so many parameters. So this is a famously known as a over-specified control problem. So we all understand the degrees of freedom. So we have only two handles, which as an operator, you can operate. Okay, so though this is a simple distillation column, that is the chemical engineering station, but when it comes to process control, this can be quite a complex control problem. So you can find out a lot of research when industry papers give a lot of details about this. So let us see how this column is managed. So we have the regulatory control, which is your PID control, a flow controller or a pressure controller or a temperature controller. You also see some advanced regulatory control schemes, means you have a cascade control. Okay, we all know some advanced regulatory schemes such as a cascade control or a ratio control or feed forward control. In this column, we see the cascade control for both top and temperature control. So is this good enough? So what are the challenges? Let us go through. So though PID control is great, it has a lot of powerful functions. There are a lot of limitations. If there are disturbances in the column, there will be, because you see these controllers are independent, okay? They are not coordinated. Only a plant operator has to coordinate. If there are disturbances, if there are interactions means if the reflux flow changes, then the top temperature will change. After some time, the bottom temperature also will change. On the converse, if you increase the bottom reboiling steam, bottom temperature will increase, and after some time, the top temperature also will increase. So this is a highly interactive system. So two temperature controllers are independent. They don't understand this interaction. So there will be a lot of cycling effect that we call. So multiple constraints. Okay, so one is instability, another is multiple constraints. So for a PID, you can give only one set point. That means a PID controller can manage only one process parameter. You cannot ask a temperature controller to control pressure also, unless it is cascading. So these are the two key limitations which would arise using a PID based controls, and most of the plants, most of the continuous plants would have these issues, but operator has to keep on managing the set points of individual process control PID controllers. So he is most bothered actually. This results in suboptimal operation. So this is the order of the day. Okay, there are various reasons why this is continued, not solved in many plants. Okay, we talked about the problem. How do we solve this? Before that, let us add some more conditions. Okay? We grandly announced that a plant operator has a lot of expectations on his operating personnel. Like any management will have a lot of expectations on the workforce. So these are the questions asked to operator. Can you always maintain the quality within the specs? Can you operate safely? Can you always meet the tight product spec? Minimize energy, maximize capacity, minimize effluents, optimize. So these are all difficult. Probably sometime you may do, but not all the time. We know that plants are run on the clock, 300 days at least on an average in a year. So every minute, if these conditions have to be satisfied, it is not possible using PID control or advanced regulatory control on a sustainable basis. So this is the trigger point for the next generation of technology. So what is that? It is called advanced process control technology. Of course, this advanced control is slightly a misnomer, because probably in the 60s they called PID control as advanced control. After 10 years with all this advanced regulatory control as your computing powers. See, this technology evolved with improving computing power and communications, especially signal transmission. And so that, please keep this in mind. So the regulatory control, advanced regulatory control like cascade, H power ratio. Then came these computers and all the industrial control systems. Then the industrial control system was called advanced. Later came the model predictive control. Okay, so that was called advanced. Then after came the real-time optimization schemes. So I will show you the layered control approach. So this advanced is always a relative word, and it is always context sensitive word. So what is advanced process control? So rather than that, let us use the technical word multivariable predictive controller. Multivariable because This has multiple inputs and multiple outputs, whereas EID has a single input, single output. So predictive because you have a model. Okay? This model is giving the power of prediction. And what is this model? We will see that. Followed by a soft sensor or inferential for product quality. So you have a predictive controller plus a soft sensor. So this is what is the technology. And I would like to underline that both of these technologies are data driven, developed using the plant data. So our common point here is data analysis. So if you have any questions, feel free, because I am sounding I'm the only guy talking here. Any questions? Okay. Go ahead. See, process control is feedback control. So feedback is essential. Closed loop is feedback. So your questions will allow me to guess whether I'm talking sense to you. Okay, so I will go ahead. Oh, this is a very famous technology being used last 30, 40 years. And this is very much applicable for highly interactive processes and multiple constraints. Okay, now you will understand why we call this as a multivariable. And very popular in refining and petrochemical processes because there is a lot of dollar benefits, monetary benefits. Okay. So one fundamental question may come to you. If we are using this, don't we have to use PID? No, sir. PID is very much important. That is part of the game. That is still the workhorse. So whatever we do is on top of the existing PID and all the cascade, feed-forward, ratio control schemes that we have in the control system. So the success or failure of this advanced technology depends on the basic building block. That is your measurement, final control element, and the PID control. So that is very, very fundamental. How it happens, we will see. Any questions? So I'm trying to provide you a picture of what happens when you have a plant operator trying to maintain a process parameter, let us say distillation column temperature. So how he is maintaining temperature? By adjusting the reflux flow. So he does adjust the reflux flow maybe once in 20 minutes, once in 30 minutes, because he has so many other jobs to do. So when he is doing it, he will naturally induce some variations in the top temperature. And you see in the first part of this plot. And sometimes this temperature can cross the limit. That means he has violated the limit. So you can interpret in terms of statistics of this data that there is a lot of standard deviation. Okay, so now let us bring in a technology which will reduce the standard deviation. Now we are talking about statistical process control. Reduce the standard deviation first, and also push the parameter to the limit and don't cross the limit. Of course, we have crossed, but not so much. So this reduction in standard deviation, okay, which can be estimated by data analytics or doing the statistical analysis, is what is resulting in benefits. Okay, so statistics or data analysis is behind the monetary benefits in this technology. That is why we are presenting in this forum of data analytics. So this will be huge data, and I'm talking only about temperature. There'll be hundreds of parameters, and this data will be for, let us say, 6 months, 8 months, every minute. So you can then imagine the volume of the data that we are talking about, and the power of tools that is required to make the right assessment, the right analysis, and the right judgments. Of course, when we talk in terms of process parameters, we want to maximize. What do we want to maximize? Throughput or feed, products, and we want to minimize. What do we minimize? Energy, steam, or some flaring. Flaring means some gases are let off into atmosphere. We want to minimize. So there is an optimization component. Okay, so this is control plus optimization at real time. Okay, so this is sum and substance of what happens with that. What is the outcome of a model predictive control? If you have questions, please let me know. Otherwise, I will keep moving. I talked about layered control. So the first layer, the most important, is the measurement, sensors. Simplest is the flow. Flow is a very common sensor that you need to have for flow control, temperature control, pressure control, level control. This is a common point. Then the final control element itself, it's the pneumatic valve, which is air operated. Now you have thousands of sensors, you have hundreds of final control elements. They are all connected in the distributed control system, that is the industrial control system, wherein you have configured all these PID controllers for flow, temperature, pressure control. They're very fast acting, you see, 250 milliseconds is the execution. When you say execution, it is the read-write of the data. You read the data. For a PID control, you have a set point. So check the difference between set point and the process value. There's a difference. Give the output to the valve to open or close. So this execution happens at the speed of 250. So we have a question. I will take it a bit later, how AI can help. Okay. So how to reduce the offset? Okay. So offset is typically handled in such industrial control system using the PID controller tuning. The main parameter for removing the offset is the gain or proportional bandwidth together with the integral. Okay, so most of the industrial controllers are PI controllers. Though we famously study the PID equation, the derivative term is only used for systems which have inherent process delay. For example, furnace. If you want to increase the furnace temperature, furnace is a huge equipment. So it will take a long time. So if you want to speed up, then you include the derivative so that more fuel is given initially and then taken back so that the process comes to the new set point quickly. It is like while we boil the milk, initially we just turn the knob of the gas on a high, and as we progress, we slowly turn it down. Okay, so this is typically a derivative control, but for your understanding, most of the industrial controllers are PI controllers. With the PI, the offset can be eliminated. The integral will try to help the gain term, but if you overact on the integral, there can be oscillation. So this is all will go into the PI tuning. We will not discuss that here. So on top of this regulatory and advanced regulatory control, you have the advanced process control or model predictive control. So it is important that you must have this DCS, distributed control system, and handshake this model predictive control with the control system and control system. And again, the read and write has to happen. The read is all the plant data and write is all set points. Set points are for the PID controllers. First, we will have an operator running the plant manually, adjusting all the set points. Once we have the model predictive control, the model predictive control is like a smart operator. It will calculate the best set points for all your temperature, pressure, flow, etc. and download the set points. This is what happens end of the day. So this runs every 1 minute typically 1 minute. So a model predictive control is for a process unit, but you understand that there will be many process units in a refinery or a petrochemical plant. So if you want to manage all these process units together, then you have the next layer of optimization. So this is the layered approach, and the topmost layer is mostly using a steady state model or a model constructed from the fundamentals of chemical engineering, because the balances are very important. Whereas your model predictive control is a dynamic model based on data. So it's a data-based approach. The topmost layer is basically a chemical engineering first principles, like you have reaction kinetics, heat balance, mass balance, etc. So as you know, as you go up the ladder, the execution frequency is lowered because you need more time to calculate, converge, make sense out of the decisions, and then download to the lower layer. So this is the very popular process control layered approach in plant operations. Very popular in continuous operating. So I see some questions, so I will try to answer at the end of this presentation. So we talked about a multivariable process. Okay. So on the left hand, we have inputs. On the right hand, we have outputs. The inputs can be adjusted, which are called manipulated variables, MV, or there could be disturbances. The disturbances can be measured or unmeasured. So unmeasured means what? There's a sharp rain, and because of which the column pressure changes. So there is, of course, there are rain gauges, but they are not integrated into the plant control system. So that's an unmeasured disturbance. So the outputs are related to the inputs, and there are multiple relations. Okay, a change in any one can affect the other output. So this is what we call it as a multivariable process. Multivariable in terms of inputs and outputs and the relations. So what those relations are, how do we define them, how do we find them, is the next topic. Again, we will come back to this simple distillation column, and let us identify the inputs and outputs. Okay, so here the feed which is entering the column is identified as a disturbance because there is no control. So if you cannot control, it is expected it will change by itself. That becomes a disturbance. So top reflux is one handle, bottom reboil steam is another handle, and the bottom flow from the column is a third handle. So they are called the manipulated variables. That means you can adjust them and control what? Top and bottom qualities. And there is one more product here which is taken out at the middle of the column. We can ignore this for our discussion. Top temperature. Why top temperature? Because that will influence the top quality. Okay. Bottom level. It's important to maintain the level to help the mass transfer. So the basic minimum level has to be maintained. And similarly, to maintain the level in the overhead drum. So it is important this valve doesn't open fully or close fully. Level control for this drum. So these are the critical parameters of the process which has to be controlled. So if you can visualize the process from the chemical engineering perspective, you can understand this reflux will have relations with CV3, CV2, CV6. This reboiler steam can have relations with bottom level and bottom quality, and of course on the top qualities also. And the disturbance can hit both top and bottom. So this analysis has to happen. From chemical engineering perspective, of course, it's very easy to say this, but we have to look at the plant data, a huge amount of data. Then we have to arrive at these relations. So that is the data analysis to develop the models for a model predictive control. So what do the models look like? So there are so many relations. Each relation between MB and CV is a model. Okay. So how do we get this model? What is this model? So before we go to the model, we will try to understand how this model predictive controller will work. This controller will utilize both the past and the future data of the plant. It will look at where the outputs or control variables are with respect to the high and low limit. It will also look at the past moves of the manipulated variables, what has changed in the past. So at present, it will always calculate if these movements of the inputs happen, what is going to happen for the output. So how can you predict this? You can predict based on the model. That is the power of the model. So probably you will predict into next 1 hour or next 2 hours or next 10 hours. You have seen these weather predictions. They give you like 1 hour, 6 hours, 8 hours, 1 week, 1 month. So as you go far into the horizon, that's the word we use, the accuracy of the prediction probably will come down. It is obvious for you. Why so? So if the control variable is predicted to be outside the limits, then this model predictive controller will take action and it will make a plan. It will plan to move some of the manipulated variables and it will ensure these movements into future. See, please remember the right side after k time, it is all future. That means it has to look at future considering the past. Okay, so this data is split data actually. The very special nature of this MPC, it has to look into the future data as well as past data and make all the proper calculations. So this happens every minute this happens, and this happens based on the plant measurements that is continuously fed to the APC application. So let's move forward. That we know that we have a feed-forward control with multiple outputs being predicted. So that is the summary, the feed-forward. So if you want to know what will be the performance when I turn on an MPC, so the left part is an operator. He is using DCS, a plant control system. As expected, there's a lot of variations. Okay, about 4 degrees, 2 degrees. You say, what is so big about it? But for a plant, even 2-degree fluctuation can matter. And you see how fast these disturbances are happening. So when you put APC, these disturbances, they calm down. The bottom part shows you the error. Okay, you see the error or standard deviation has been significantly reduced. So this is the power of a model predictive control versus a DCS based PID control. Of course, you need an operator to manage both the situations, but it is very straightforward who is superior. So we'll come back to this topic later. We are now looking at only one parameter, which is temperature. Imagine you have to look at 50 temperatures or some 60 qualities. Again, we will get back to data analysis. Is this good? Is it giving you the best performance, etc., etc. So we will revisit this after a few topics. So We will go back to the very fundamental of this technology, the model. Model is constructed using plant data, and that plant is continuous plant. So we have independent variables and dependent variables, inputs and outputs. And the model should reflect the dynamics of the system. That is the basic definition of the model. So there are two perspectives, the model and controller perspective. For the model, it is the inputs and outputs, independent and dependent. For the controller, it is the control variables, the outputs of the process versus the manipulated variables and the disturbance variables. Okay. So this is the model for a model predictive control. So how do we get this model? So we are now talking about dynamic model identification. So this is a very famous experiment which bachelors they do in their 5th or 6th semester. So this is a step response test, and for a unit change in input, you measure the process value and also the time taken. So this gives you the parameters of this model, which could be a parametric model, and the key parameters are delay. There's a delay in the process, there's no response. There's a change in the process, that's a gain, and the time constant. Time constant reflects how much time this parameter takes to settle down. So this is the very fundamental structure which for any dynamic process you can identify. Even physical observation of these trends can let you know. But how do we estimate these parameters from the data, from the statistics? That is all about model identification, and very advanced techniques, data analytics techniques are behind this identification process. So why do we have to have a dynamic model? Because your process is dynamic, and if you want to control the process parameter, we would like to have a model, and the model should help to adjust the manipulated variables such that the process parameters are always within the specification. To put it, if the top quality is going out of the limit, since you have the model, since the model has gain, so the model can reverse calculate or invert how much reflux has to be changed to ensure the top quality is brought back within specification. So this is what we mean by invert the model. Once you have the model, you use it in a reverse way. The controller will use it in a reverse way to calculate how much reflux has to be put into the column to ensure the top quality is within specification. So this is how this technology works when it is deployed online. Any questions? Okay. So how do I build this? Of course, we already saw this step response test. You can also build using a dynamic model which is constructed from the fundamental mass and energy balance. This goes into differential equations. It has to be dynamic model. And it is not easy to construct such models for a very complex processes like refineries, because the input itself, this crude oil, has so many components. So writing all these component balances for heat and mass is very, very challenging. That is one part of the problem. But to solve this at real time, say now 1 minute or 250 milliseconds. So this model is developed using a software. So I will show you how it is done. I will demonstrate that. So instead of going the very hard way, also have to think about the maintenance. In fact, it is always the big question: how easy it is to maintain this technology or software. If it's complex, people won't buy. So we will use a technology called system identification. So there is some background noise. Can you please mute if you're not asking any question? So what is system identification? So of course, process knowledge is important. So we make a design of experiments because there are many inputs to be changed. Then execute, change the inputs in some order. And before doing this, you should know which of the inputs in the process are related to the outputs. That means you have to a priori identify the model structure. Then using the data collection is very important while you're doing the test. Collect the data and estimate the parameters. So this is, you can say, curve fitting or best fit of the data into the structures that are known. And then validate the model. Model validation is use part of the data, check how the predictions are using the model. The plant measurements and the model predictions should match. Then you have got a perfect model. So this is a work process. Then this is how the steps are done for a process. Imagine this is the reflux flow, which is increased and decreased with the different magnitudes. Okay. Once you change the reflux flow, the top temperature also will change. In this case, both are changing in the same direction. But for a reflux to top temperature, it is the opposite direction. That means you have a negative gain. So this is what is a step test that is necessary to generate the dynamic data for dynamic model identification. So how do we do this? Of course, you can do this manually, but in an industry scale, we use softwares. So that software I will show you how we do that. So we also have some techniques automated because you have to do these steps many a times, repeatability. Okay. So pseudo-random binary signals. This is what is PRBS stand for. So such signals are generated, injected into the process. So there are different techniques for identification. One popular technique is finite impulse response. Okay. The finite impulse response, as the name says, there is a unit change for the process input. And the output response, you make it into many small pieces and then do an integration. Okay. So the output of the process is a summation of all the changes that happen for the process over time, and you have the coefficients to represent how much the process has changed. Okay, so this is the mathematics behind the finite impulse response, and this actually models the process as the process changes. Okay, so that is the advantage of a finite impulse response. So this shows in simple terms how these coefficients are calculated for a change in input. The independent input is changed by 3 units and the output changes, it slowly changes 3, 12, 18, 21, then stabilize. Okay. So the difference in values at each segment is would what give you the coefficient. Using these coefficients, this whole curve is constructed. Then we have the equations to represent this model, and basically you will end up with simultaneous equations. So these are all arrived using simple regression. So this mathematics should be quite well known to you. Okay, so that means there's a lot of math behind this model development, and this has to consume the continuous process data. So we also have a very popular technique called parametric model. Unlike FIR, which represents the process as is, parametric model is the approximation or best fit. So here the fundamental parameters are gain, bit time and time constant. This is what you see in a step response test. So there are very famously used forms of this transfer function. These are all transfer function models. First order, second order. We don't use beyond second order because of the complexities. We try to approximate. Okay, so there's a lot of approximations around. Approximate to a second order. Ramp is for a level. Level means it is always increasing, not decreasing. So there are zero gain models. For example, your top temperature of the distillation column, if it is cascaded to reflux, if there is a change in the input, the response will be normally zero gain, because if the temperature changes, then the reflux will start acting because it is cascade. So it will bring back the temperature to its original value, set point. So it's a zero gain. So these are the mathematical representations, and we would see this for each of these output change. Okay, this is the form of the output. You please note that there is a step change for the input. So these are the responses that you would expect when you do a step test on a multi-component distillation column. Okay, it could be first order response, it could be second order response, it could be overdamped or underdamped, it could be inverse response. Okay, many times you will see inverse responses because of a lot of interactions in the process. You would also see the ramp. Ramp is for level, I said. If you increase the outlet flow or inlet flow, that level will either increase or decrease. So these are the popular fitting techniques or the model forms that are used in the industry to construct the multi-input, multi-output model matrix. So I explained about the zero gain model. So this model, which is very different from your PID model. If you remember your PID equations, okay, you have gain, integral, and derivative. Here you have gain, time constant, and dead time. Okay. So this is the fundamental difference in the model. So these models as a matrix of inputs and outputs will result in the expected benefits. We talked about a lot of expectations: quality, safety, constraints management, throughput maximization, energy minimization. So this model is very powerful when assembled in the right way. Okay, so the models coming out of the dynamic data, okay, and developed using the right analysis tools, assembled in the right configuration, would give the dollar benefits. So that is what it stands like, from data analysis to a model like this to an assembly of models, which results in a lot of benefits for the industry. So this is in a summary about the model predictive control. But just the model predictive control is not enough, because we know the quality sensing or measurement is very important. Because if the controller is maximizing without looking at the quality, or if the quality specifications are violated, the product is useless, it is off spec. So quality measurement becomes important. So how do you build this quality estimator or soft sensor? Of course, you use your process conditions. So now you are in the domain of chemical engineering. You know that the top quality is a strong function of top temperature, top pressure, and some bias. So such correlations are developed. So how do we develop? Of course, again, we have to go back to the data. So the data analytics is all around. Okay, so the summon substance of development of this technology is data analytics. So we use the lab data, we use the process data, and we develop these correlations. And the technology behind this is regression analysis. So this is the model. Okay, so this is mostly a static model. That means temperature, pressure, reflux flow. So you can imagine a arithmetic equation. Some A times temperature, B times pressure, and C times reflux ratio will give you the product quality. So it's a simple calculator. Even using Excel sheet, you can do. Okay, that is very much possible. But you need a full-fledged technology to safeguard online performance. That is where Excel sheet is just not enough. To build a model, Excel sheet is enough, because we talked about correlation and the regression analysis. So the quality can be measured by lab or from online analyzer. Lab means once in a day or once in 8 hours. Online analyzer means once in 1 hour or once in 30 minutes. So between these two times, there must be quality measurement. That is what soft sensor will do. And the soft sensor is not so robust because you are using data to build this. If the operating conditions change, then the quality predictions can go off. So that means it needs constant upkeep or calibration. So the calibration is using this lab or analyzer. Okay, so this is the essence of a soft sensor. And what is the performance? So we are looking at a melt index. This is from a polymer plant. So the blue line shows the analyzer value, and the red line is actually the prediction of a soft sensor model. You see that the soft sensor is able to predict as close as the analyzer. Analyzer is real, that is the ultimate. But the soft sensor, which is very cheap because you just have to have a calculation, whereas analyzer is expensive, it has to be maintained. You see how well this soft sensor in red is following the blue line, which is analyzer values. So if this performance is accepted by the plant user, then you can do away with the analyzer. Okay, so there is a lot of benefits by this soft sensor technology. So with this, I would try to show you the demo. So let me change my screen. So I will request you to turn off the video. Please stop the recording because these are all commercial softwares. So please don't record this part of the session. I will tell you when you can start. If you're recording this, request you to stop the recording. So are you recording this session, Professor?
Sir, sir, actually in between it is, we are not, it is a YouTube streaming, sir. Hello, it is audible, sir?
Yes, yes.
It is actually going in YouTube streaming, and I think in between it is tough to stop and re-record, sir. Um,
Okay, so are you posting this video on YouTube?
yes. Actually, it is like online streaming is going on, sir, in YouTube. Are you posting it in YouTube? Yes, sir, we are posting it.
So
So
after
if it
the
is more
session, I'll request you to remove this because these are all with confidential contents. So,
okay, sir, we will remove it.
okay, so please don't post it in a public forum. Then I will have to pay some legal consequences.
So then it is better, no, sir, you can just tell the content, or if possible, only the content you can reveal it, sir. Because I don't think so, like in future, we can remove this particular content alone from the entire day streaming. Sir, is it audible, sir?
Yeah. I'm thinking how to manage. Anyway, I will quickly show you this.
Yeah, yes, you can move it fast, sir.
So we have a lot of measurements from the process, the flow, the temperature level, etc. So we have the data from the process. which is step test data. You see the set points are changed, for which there is a response of the process. So there is continuous data, and this data is used for developing the model. And these are the models that you get. So what is this model? Basically, it is a parametric model. Okay, so this is a step response model, so which has the parameters of gain, delay, time constants. Okay, so this is a second order model. There can be several model orders, which I explained. So you see that whatever you study as part of process control, that is being used on a day-to-day basis. Using data analysis, these models are the best fit models. Okay, so you see that the model is perfectly matching with the process data. So this gives us the confidence. Yes, we can go ahead and use this model for plant control. So this is a perfect match. See here, what we are trying to do is compare the model predictions, which is actual plant measurements. In this case, this is the temperature. And this shows a perfect agreement with the process. So finally, we assemble these models like we see here. This is the assembly of models. Okay, so these are the inputs. Inputs are your manipulated variables, and these are the outputs, the control variables. So this is the model which is used at real time to control the process. So how is this deployed? I will show you also how this is deployed. So this is the process. You will see the distillation column with lot of control loops. These are all PID controllers, a flow controller, level controller, temperature controller, pressure controller. You see they are all in auto. A means auto, C means cascade. That means you as an operator, you can change the set point. Okay, you can call this faceplate and you can change the set point. It is 30, I can change it to 31. So what happens? The output changes and slowly the process value will catch up with the set point change. So this is a typical operation, manual operation. Since we described that this is a challenging process to control, multiple constraints, very less number of handles. So we will look at a model predictive control. Okay, so how does a model predictive control look like? Okay, so this is an application which is running in another computer, which is connected to the control system computer. That means you have two softwares running in two separate server grade computers, and they are connected by communication protocol. It's called OPC. OPC protocol, that is the data handshake of plant information to the application information. So this controller is in standby. What does this controller look like? Okay, so it has some manipulated variables, which low limit and high limit. It also has some control variables with low limit and high limit. That means this is set range control, whereas your PID is a set point control. So we will turn them active. We will see what happens. We have to turn the controller also active. So in nutshell, what happens is all these manipulated variables, please remember they're all PID controllers in the control system. Now that PID controllers will be actually controlled by this application. Okay, so that is the APC control or MPC control. Check. So I have to activate all these inputs. So that so you will see some transactions, all these DCS loops. DCS means control system. So now they will be taken into control. Means as an operator, you can no longer change the set points. I will show you that. And all the set points will be controlled by this APC application. So it will normally take about 30 seconds for the handshake, the exchange of this information. But once connected, every minute, it will try to do the transaction. Means check all the limits, check all the conditions, then try to control. Okay. So you see, it is making a move. This move is to the PID controllers in the DCS. I will show you that. You notice that this A has been replaced by R. You will see several R's. This is the bottom heating. This is the top temperature. Okay, this is the bottom flow controller. So this R means remote. That means now instead of operator, this MPC application, this application try to control the process. So how it will control? If the control variables are going outside the limit, it will move the set points to ensure they are always within this the specifications which are specified for the control variable. Okay, so this is a quick demo of the industrial application. So we use this software to develop the model, and this software has a lot of powerful tools to generate the model identification. So there are a lot of analytics behind this. So due to confidentiality purposes, I cannot show you all the details. And of course, you are also going on YouTube. It's a bit of a disadvantage. Anyway, I will have to go back to the demo. So let us just step back. If you have any questions on what we discussed and demonstrated so far.
We have actually queries in the chat, sir. If you wish, you can clarify now or at the end of the session, sir.
Okay, okay. If you have questions, please key. I will quickly take 5 more minutes. I will complete the remaining slides and we will go to Q&A. Okay. So let us say we are running this controller. Okay. Auto tune. Yes, I will explain. If it is a naphtha stabilizer, we can count the outputs, we can count the inputs. They're not so many. But we have to address the questions which are here. Output variables are within the limits. Whether the manipulated variables, they are the handles, whether they have enough room to move to control the outputs. Whether the disturbances are normal. If they are going up and down, they're crazy, then this controller cannot help. So how do you find out? Of course, you look at this picture, you can find out yes at this moment. But if you have to make this judgment over the last 1 day or 1 week or 1 month, obviously you have to do some data crunching. Okay? So imagine you have a model predictive control with 33 inputs and 28 inputs. It's too much of a manual work. That means again you have to go back to data analysis. So what are the typical metrics that are looked at? For input, whether MB is on or off, how many times the limits are changed, whether there is any wind up, whether there is any violation. Same statistics for CV. how many times your quality went out of the boundary, how long it stayed out of the boundary. So you are calculating with respect to time on this. That means you have to arrive at the statistics using the data analysis. So there are very powerful functions like outlier detection, checking the bad data, or data which has become static, or there are spikes in the data. So all these have to be negated. So you cannot simply run the statistics and say, okay, take this. This was what your average value, and this is how it has changed. That has no meaning. So simple statistics, of course, is useful, but unless you do the uh, analytics on this data, it is useless. So the performance monitoring itself is a very big area for research and data analytics. Okay, and this kind of reporting is very, very important to check whether this controller is working properly. So what can go wrong? So one simple thing we understand is any chemical plant, let us say you have a catalyst bed, it can age. That means the performance can deteriorate with time. So the models that you developed, the dynamic responses of the process that you estimated using model, the very beginning of the year, the plant response at the end of the year could be significantly different. That is very obvious for chemical engineers. So that means over a period of time, there is a degradation. That means there is a mismatch between the model and the plant. Okay, we call this as plant model mismatch. So this is one of the key KPI to measure. Okay, and it's not easy to measure this plant model mismatch. That is part of this performance monitoring. Okay, so with this, I move to the last part. Okay, so where this AI/ML techniques are now forcing their way into the whole technology. Okay, so this is about the nonlinear model identification. See, we know that all processes are nonlinear in nature, but using these techniques like FIR or transfer function, we try to approximate. Okay? That will work for most of these processes because there is a feedback. This is a 1-minute controller. Its feedback we can manage. Okay. If there are any model uncertainties, somebody asked the question, how model uncertainties are managed? Okay. Let us say the model says the temperature is 100, but the actual temperature is 100.5. So the 0.5 is accepted. Versus if you say, look, I am predicting that temperature is 85 versus actual measurement 105. This is a big mismatch. So this much of uncertainty cannot be tolerated. Okay? Whenever you develop a model from dynamic data, so the tool provides you what is the uncertainty. Okay? How much sure are you in predicting 100%, 80%, 90%? Normally, most of the models with 90% accuracy, we agree. Okay, that is the uncertainty because in any process there is a lot of noise, there is a lot of unexplained disturbances. So we have to be bit giving some margin for that. So 90% accuracy we accept because this is a 1-minute feedback control. Okay, that is the response for the uncertainty. So there are uncertainty bands. They show the uncertainty bands. If they are very narrow, then we say, okay, no problem, let me go. So let's come back. This polymer processes were highly nonlinear. Okay, now, what do you mean by that? The process gains. Okay, so far whatever we discussed, they're all linear processes, linear models, linear controller. That means for any operating condition, if you change the reflux, the temperature will change by 0.75 degree. That is for sure. Okay, whether the throughput is 50% or 80%, but the non-linear processes are not like that. The gains will change. Okay? The dynamics will change. So this, though we have a feedback control, it is not good enough. So what we have to do, we have to have a nonlinear model to handle such processes. So how do we build? Most of the technologies commercially available, they use this first principle models. That means it's a very elaborate procedure. And a lot of efforts goes in, maybe 1 or 2 years to build a model, dynamic model using first principles, and not easy to maintain, especially when there's a plant mismatch. So such applications will not be popular. So the nonlinear model identification techniques using data, like the data what we talked about, that is still a work in progress. So this last statement is what is the trigger point for AI/ML techniques. Okay. Of course, my topic is not to explain AI/ML techniques here, because AI/ML techniques are just getting into this research area of this industry. They are not very well established. They're not very well proven, not very well accepted also, because this industry is highly risk averse. Okay, you cannot make some predictions which are not consistent. Okay, this is the problem with many of these auto tuning techniques what we have. Okay, auto tuning techniques are fantastic, but at real time, people don't want to do such things, because there could be a risk of wrong predictions or wrong action. So the technology is good, but the acceptance is low because of the risk factor involved. The safety of the plant is paramount. Okay. So with this, I will stop my explanation. Let us spend some time on questions.
மேடம் முதல்ல இந்த ஸ்ட்ராட்டஜி மாத்துங்க மேடம், அதனால தான் நம்மள தட்டி சொன்னா நான்.
Let me look
5
at the
minutes, sir.
chat window.
Yes, sir.
If you have any further questions, please key in. What is the role of AI in process control? How it could help us? See, there are two topics here. One is AI, another is machine learning. Machine learning is all what we talked about, using data. Could you please mute yourself if you're not asking
Yeah.
questions?
Yes, sir. I have muted the person who was like having created that background noise.
Okay,
You
thank you.
can proceed, sir.
Yeah. So AI is artificial intelligence. Okay, so artificial intelligence is you have seen some patterns and you have observed these patterns over a period of time. Like you are an operator sitting in the plant last 10 years. So you have a lot of understanding, you have a lot of intelligence about this plant. So how do you use this intelligence to take actions? That is artificial intelligence. And to develop some techniques or models using the data, that is machine learning or data analytics or big data analytics. So AI can definitely help in process control. Let us imagine a situation. There are different kind of fields. This is very common in a refinery, oil refinery, because the oil itself is a natural material. It can come from Gulf, it can come from Venezuela, it can come from Bombay High. And the same raw material need not have the same composition when you process after 6 months. So that means you have different patterns of the input, and each pattern will give a significantly different outcome or yield. Okay, suppose say you have collected a lot of data, okay, and you can develop some patterns, and based on the conditions you can adapt to these different patterns. Okay, in my opinion, that is artificial intelligence. That means as an operator, because people have been doing this is nothing special. Whatever people have been doing, can we capture as a pattern? Okay, and then that you formulate as a rule or a model using machine learning, and then you deploy this as an application. So this is where this artificial intelligence can help process control, especially this multivariable control. So it will be of great help. And my colleague Sri Sandeep Adiga, he would explain in further detail. I'm only giving you a summary of this because my topic is not about explaining this, but to build the context where we stand today from 90s. Okay, so that is the answer to Professor Shashikala. Okay, so Shiv Kumar, I think we know each other. So how AI can be implemented, understanding the reactions. So Shiv Kumar, I will take this question to my colleague. I don't think AI has been commercially deployed. Okay? So AI still is in nascent stages. rather than giving you any response, I must say this where it stands. So people are using to predict first. Okay. So if the predictions are good, and the predictions are good for all conditions and all types of processes, especially such critical processes, then definitely we can use a model based out of AI. But as on date, we don't think AI is used for such control purposes. AI is getting popular. It is getting into these soft sensors because it's all about predictions and you can always compare. Okay. If you don't like it, you reject it. But closing the loop, real-time control, I think it has to wait. It has to wait. That is the current situation. So that is my answer to your question, Professor Shikum. So model is developed using software. Of course, I showed you the software. So some of the key technology players in this area are Honeywell, AspenTech, and Yokogawa. And most of these technologies, they differ, but the methodology is same. That means you use the dynamic data, develop a finite impulse response model, use this starting point and convert that into a parametric model. By parametric model, it'll try to approximate smooth responses. Okay, so final model is most popular as a parametric model. So software is used, and the software will help you. So it's a tool. Okay, so we don't have to do any coding. You just plug in the data, you get the output. But analyzing the results is very important. As a control engineer, as a chemical engineer, it's important to do the analysis. The data, what you feed in, and the output that software that gives you. If that factor is missing, then you will end up with some bad implementations. It means the application quality will not be good. Okay. How auto tune works? See, let us talk about this auto tune for a PID controller. So it is popular as a self-tuning controller. Okay. So what is tuning all about? Let us look at. Let us say if we are doing the tuning for a flow controller. So first, what we do, we will put the loop in manual. We will change the output or the valve opening, and we will see how the flow will change. Okay. Normally, within 10 to 15 seconds, this flow will change once you open the valve by 10% or close the valve by 10%. Okay. So we also check whether the changes are linear, because for many of the valves, the 0 to 5% or 90 to 100%, the changes are not linear. So then we close the loop. By making this open loop test, we can figure out what is the gain of this process. And we also know, because this is flow, within 10 seconds it will change. So we also have a eye on integral. So this is a manual tuning versus auto tune. See, what is auto tune? The auto tune basically changes the tuning parameters. What is the tuning parameter? It is your proportional band or gain. It is the integral. A derivative is normally not used. I mentioned earlier. It is a PI control. Okay, so if auto tune has to work, what is the basis? The basis is again a model. So if you can have a good model of this process, then this auto tune works. But what is the flip side of it? The flip side of it is the model that you construct for a PID can have only one or two inputs. That means PID is a single input, single output controller, CISO model. Okay. So we cannot have too many, which could happen as a disturbance for the process. Okay. So the technology of auto tune is great, but when you deploy it online, the disturbances that could happen are the disturbances which are not accounted for, because you can give only one or two inputs, as I mentioned. This is a CISO model that can derail. So because this industry is risk averse, they would rather say, no, 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 I don't want to try this. You as an engineer, you please try it, but I don't advise you to keep it on. So because of this conservative nature, and also for the safety purposes, this auto tuning is not popular. That doesn't mean that this technology is not good. It's not possible. I explained the model uncertainty. Last question is KF and EKF. Oh, yes. KF, I think you are talking about the Kahneman filter. Okay, so see, the filters is all about noise handling. Okay, so as we talk about this technology, it's all about data, and this data is nothing but measurements, temperature, pressure, flow. There could be some noise in the process. This noise can be big, this noise can be small. Okay, so it is important to characterize this noise. Okay, if this noise is very big, that is characterized as a event. Okay, because these are all measurements, engineering units are very helpful. So we can always categorize, look, if this change in the process is more than this degree Celsius or distance per hour, then I will consider this as an event. Okay, let us say there's a change very small. Okay, I would say if it is less than 0.25 degrees, I would characterize this as a noise. Okay, so we use Kalman filter to handle noise. Okay, so Kalman filtering is one of the popular techniques for calibration of the measurements. We don't want to feed some noisy or big changes or spike data into this application because it will calculate some crazy numbers, crazy outputs. So yes, AF and EKF is used, and it is one of the most popular technique for calibration of measurements.
And now, if participants have any doubts, you can raise your hand so that you can speak directly with Venugopal.
Yeah, please.
As now the session is open for discussion. So if anybody is willing to ask questions directly, can raise their hands.
So I have a question to the audience because I can't see you. Would have
Okay,
been nice
please.
if we are in person. So I tried to share a lot of information. First of all, was it useful to you? Was it to the context? That is my question to you. So anybody can respond. Okay. Fine. So to the context, because the context is data analytics, and this advanced process control is all about data, process data, dynamic data. So I thought I would make this pitch. And also, I try to introduce you to the challenges and also the open areas. This nonlinear model identification, performance analysis. All these are all open areas. And there's a lot of applications to be developed.
So thank you, sir. Thank you for the enlightened speech on advanced control and optimization. Even the possible real problem arises in the process and key solution is being discussed with advanced techniques and even with software demo. So it's great honor to have you in Atal FTP program on behalf of organization committee members of MBJ College of Engineering. We thank you for sparing your valuable time with us, sir. So you want to tell anything, sir?
Thank you very much. And if any of you for your research or your further activities, if you have any question, always feel free to contact. So let me share my personal email ID. This is my email ID. So you can reach out because I'm sure some of you would be working in this area. Some of you have already tried to solve these problems or try to understand more, whatever it is. So you're most welcome. You can contact me.
Thank you, sir. Thank you so much, sir.
Thank you very much. And thanks for your time.
Thank you, sir. Now for this session, the feedback have been posted in the chat box. So participants kindly fill the feedback, though it is mandatory to calculate the percentage of attendance. So please, the feedbacks have been already posted once again in the feedback in the chat box. Kindly fill the feedbacks. And the next session start by 11:30 a.m. So Kindly join 10 minutes earlier. So the session is by Gayan, scientist from CSIR on application of big data and artificial intelligence in chemical science and engineering current scenario. So kindly join 10 minutes earlier for the next session, 11:38. Thank you.
Okay. Okay. Thank you very much. I will leave the meeting. Thank you.
Yes, sir. Thank you, sir. Thank you so much.
Hello.
Hello. Hello.
Hello.
Yes, sir.
Yeah. Madam, this is Dr. Gyanendranath Mahapatra.
Yes, sir.
Just testing.
Oh, okay.
Oh, you're unmuted also. It's working. I will sit here. But that's already. But how can I present? Share it is not.
No, this will come now. Now they have to enable you for sharing.
Okay.
As soon as, when is the time? What is the time?
11:30.
No, what is time?
11:30.
Already.
Good morning, sir.
They have to enable this thing. No?
No, this has to come. You speak now? You can speak.
Hello.
They're on mute. Speak. Oh, sure.
Hello.
Good morning, sir.
Good morning, madam.
Can you
Sir,
unmute? Can
just
you give me
wait
the share
for-
permission you asked?
Yes, sir. Just wait. We can wait for 2 to 3 minutes. Participants are joining.
Okay.
You just share your presentation so that you can
Madam.
check.
Now.
No, you want to share? Click. No, you can do screen. Click on that. Share. Click. Now this is your screen, right? Okay. Now you go to where is your yeah, view slideshow. Now everything is uploaded. Now you ask them whether they're able to see your slides, your screen.
Yes, sir, it is visible.
It is possible. Visible to
Yes.
them also. Very good. You want me to present it also? Okay, thank you. You are clear. Last year, is that last? This is my guess. You. I'll check. But you are. This is. I know it.
Good morning, sir.
Yeah, madam. Good morning.
Live as if you were to die tomorrow. Learn as if you were to live forever. With this inspired quote by the Mahatma Gandhi, I would like to start this session. I'm Sakshi, Assistant Professor of Department of Chemical Engineering, MVJ College of Engineering. Good morning, everyone. Heartily welcome to all the participants after break who has joined for this today's session 8 on third day of 1 week online FDP program sponsored by AICT Training and Learning on Data Science and Artificial Intelligence in Chemical Engineering, Recent Trends and Future Outlook, organized by MVJ College of Engineering, Department of Chemical Engineering in association with IIC and IQAS. Now we have our most renowned person, Dr. Gyanendra Nath, Senior Scientist, CSIR, 4th Paradigm Institute with us. Let me brief some key credential of his achievements. Scientist has been awarded his postdoctorate degree from Berhampur University, Odisha. Sir has more than 15 years of experience in the field of research. His research area of interest are mesoscale modeling of extreme weather events like tropical cyclone, extreme rainfall events, heat waves, and associated synoptic features. Scientist has very good international journal publication. Without any further delay, I would like to invite Dr. Gyanendra sir to deliver his talk on application of big data and artificial intelligence in chemical science and engineering current scenario. Welcome you, sir, on FDP platform.
Yeah, madam. This is a very good honor for me. And am I audible?
Yes, sir.
Yeah. So now I think I can start.
Yes, sir, you can start.
Yeah. So now, good morning, everybody. And Principal Madam and Sakshi Madam, Ashokan Madam, and guests. Basically, I know the principals are since last 4 or 5 years from MBJ College. I'm very much acquainted and familiar with MBJ College. Maybe they're inviting me on different induction programs also. It's a very advanced, and I can tell you, it's a very good institute that nurturing the education system and the value the students' future to a higher level. So that kind of credential this college has, MBJ College. And before going to start this talk about AICT training and learning program, I want to cite some 2-3 things that I have experienced with all these teachers. So now this Teachers Day is coming. So we know that there is a proverb called Guru Brahma, Guru Vishnu, Guru Deva Maheshwara, Guru Sakshat Param Brahman, Tasmai Shri Gurave Namah. So always teachers are at par with God, we can say. Their vision, their way of teaching, and they're trying to make the students' career from a mod to a particular kind of image which can show the world, or it's a character they can build which can show the world, yes, this teacher has, this community has the strong willpower, the backbone of our country, and how our teaching students are flourishing everywhere. So with this, I'm starting this technical thing. So what do you mean by data science and artificial intelligence in chemical engineering? So nowadays, there are widespread talk about data science, starting from our Prime Minister Narendra Modi ji and the Science and Technology Minister and other persons, those who are taking the headship of our science and technology mission in India. They have always talking about this data science, artificial intelligence, machine learning, and deep learning. So all these are the things which is very familiar nowadays, and they're expecting that up to 2026, India needs 5 million jobs in this data science, as their projection is like that. So how we can brace ourselves with this kind of tools and technology to nurture this technology in our student community, and we can further go ahead with taking this skill, and we can grab the job, we can be getting a good job anywhere in India or abroad. So these are very, very important issues nowadays, that everywhere scientist, engineer, technologist, industrialist, everybody is talking about this data science. And I want to make it clear from the beginning itself, I am not a chemical engineering background, so excuse me, but the data science as a widespread tool you can use any part of science, pharmaceutical science, chemical science, engineering science, mathematical science, atmospheric science, which is my basic subject. I'm regularly studying about all this mathematical modeling. Also, you can do this in data science. So there are several aspects of data science that you are trying to attack, or you are trying to utilize it in your tools to solve real world problem, virtual world problem, and basically these modeling issues related to chemical science. So I'm just trying to go for this. Yeah. So what are the science paradigm? I'll just I'll brief about my fourth paradigm institute. Actually, what it means for. Everybody knows there was a Microsoft guy, John Gray, who has written this fourth paradigm concept. From this concept, we came to know what are the fourth paradigm. Nowadays, we are going to use it. Thousands of years ago, science was empirical, describing the natural phenomena.
Girls,
Yeah, and
girls,
last few hundred years, theoretical branch using models, generalizations.
உனக்கு ஏதாவது கேக்குதா?
So all these are the
என்ன
second
கேக்குது?
phase of paradigm. And last few decades, a computational branch
அப்படியா?
simulating
வேற எதுவும் உனக்கு
complex
வருதா
phenomena.
விஷயம்?
Madam, I am
வேற யாரும்
listening
பேசுற மாதிரி
somebody
சத்தம்
voice.
கேக்குது. நான் பேசுறது மட்டும் தான்
Sorry,
கேக்குதா?
sorry, I'm doing this. I think somebody is.
வேற யாரும் பேசுறது கேட்கல உனக்கு?
Just a minute.
Yeah,
Oh,
now it's
now
okay.
fine? Yes, sir.
Yeah. So last few decades, a computational branch, and that is simulating complex phenomena like ODE, ordinary differential equation, partial differential equation, Navier-Stokes equation. These were the last few decades that computational branch, they're doing all these things. That is the third paradigm. And today we can talk about data exploration, unified theory, experiment, and simulation. So this data exploration is a very big area. It's not a small area. It's just like a ocean. So in this data exploration, data captured by instrument or generated by simulator, processed by software, information, knowledge stored in computer, and the scientist analyzing database files using data management and statistics. So all these things are coming today with more advanced cutting-edge technology, like how to utilize the big data and how to generate a simulation with using this big data and what are the interpretation. These are very, very important aspects nowadays people are searching for. And I can tell you, next coming futures means next few decades. Sorry, yes. Anybody?
No, sir.
You want to say anything? Anybody wanted to say anything?
So some background noise is coming. I'm just
Okay.
unmute who is
Okay,
there.
okay, thank you, madam. So these are the different paradigm of science that we are going through. And this today, this is the scenario of fourth paradigm, and we are talking about data science. So this is the scenario that how all scientific data are available in online. So many disciplines overlap and use data from other sciences, like raw data. Then you are going to derived and recombined data. This is analytics. After analytics or reducing the noise, then putting it on a different format of equation, solving it, and then you are going for the literature. That is the pyramid age. So go from the literature to the computation to data back to literature. So this is the formula that now this data science people they're using in a different tools and different catalog. So increased scientific information velocity, huge increase in science productivity. So why this data science issue came? Actually, I'll go on the next slide. what are the issues related to data science? It's become a pervasive data science, big data, and data analytics. It is affecting many aspects of our lives, many professional disciplines, and certainly the profession of chemical engineering. So, the reason for this is, of course, the increasing availability of data, what I was telling, by the proliferation of expensive sensors and instrumentation, new measurement capabilities. So I can give you an example. So now people are talking this universal modeling. I mean to say, what are the theory behind the birth of universe, birth of this different stars, galaxy, and planets, solar systems. So sorry, our aircraft is moving, so that's why the sound is coming little bit. Yeah.
Yes, sir.
So it's a universal modeling. I was just talking about this thing. So now the data is crossing over gigabyte, terabyte, and petabyte, and now it's on and on and on. So different data systems, different data volume, data speed, and the different data utilization. Day by day, it is increasing and increasing and increasing. So there are certain challenges. And what are the challenges? I will come in the next slide. In order to exploit the data that is becoming available, chemical engineers need to use data science methods. The questions are then, what are these methods? And what role can the curriculum play in the preparing graduates to be able to use them? So I can request all these teachers in this FDP program, all our faculty, they're my colleague, I can tell respectfully. So they should look at the skill of the students, how coding thing they're doing, what is their motivation. If at all there are some issues regarding this coding, then how it can be eradicated and how the knowledge uh, they can utilize during the time of coding or writing any program. So I'm going to the next. So what are the data science and AI? Just I briefed it. So these are the commonly divided into three categories: data management, statistical and machine learning, and visualization. These are the major part of data science. With each category are many methods and tools that can be used by chemical engineers to address data related challenges. And data management, now this is a big company like IBM, Google, Microsoft, and other big company of the world. Actually, all company has a data center from where they're monitoring all these data on a regular basis. And very precision, you can say their precision level is almost 99%. Even they have the data of a person moving from which place to which place with accuracy of 1 meter, they can tell you. So what I mean to say, so every day some gigabytes data is going to this data server, and they're maintaining it. And they're mapping also on a different scenario for the different purposes, or business purposes, or you can say they're mapping it from the scientific point of view. They wanted to get a basic information about this world, how all these things are functioning, means people are functioning and the works are going on, and what location wise, movement wise, and also keeping all this data, they're making it a application, which is useful now that you can say Ola, Uber also using this data. This Google data they are using. So artificial intelligence also is the simulation of human intelligence processed by machine, especially computer systems. So data science comprises of various statistical techniques, whereas artificial intelligence makes use of computer algorithms. So I wanted to make it very clear. What is data science? Data science is a big umbrella, and AI is a technique. AI, ML, and deep learning, DL, these are the techniques used or tools used to procrastinate or forecast what are the things can be done and what will be the future scenario. And even if I can tell you, modeling part also similarly important. But again, there is a contradiction between modeling, statistical and dynamical modeling, and this in data science. People are telling that it's a huge debate. We should not go to that contradiction debate, but it is a huge debate that whether data science, studying the pattern, applying different statistical techniques like principal component analysis, like regression analysis, correlation analysis, whether we are reaching in a conclusion that strongly we can say this will be the forecast, this will be the model achievement and model capability, and model can capture certain events. Or we can use the long-term statistical data for years and years, 100 years data, and we are finding the regression. And we can say, using this regression technique, that next decades or next 2 decades or 3 decades, that can happen, something can happen with any events you are trying to simulate. So data science doesn't involve a high degree of scientific processing as compared to AI. So this is the basic difference. You should not get confused between AI and data science. So data science is a big umbrella. So next I can go management. So it reports to tools and methods to organize, sort, and process large, complex, and statistical data sets. So it's very important that how we are organizing, sorting it out, and processing it to enable real-time processing of streams of data from sensors, instruments, and simulations. There are several sources of data now we are using, like instruments data, like different sensors putting in IoT, and real-time processing data also. We are just putting some data, we are observing it in the real time using sensors. Instrument I can say you have in chemical engineering, there are several instruments, but in our meteorological science, I can say rain gauge is there, hygrometer is there, then ceilometer is there, LAI is there, and temperature measurement thermometer is there. So wind vane is there. So like that. So different, we are measuring different parameters with time and spatial zone, and we are finding those data, recovering it from the loggerhead, and we are keeping it. There is a telemetric transformation system that we are getting all those data directly from the in situ position. I mean, wherever this instrument is there, sitting at the laboratory, we are getting all those data on a real-time basis. And after that, storing all this data, and you can say sorting, organizing or sorting, you can say, we can visualize what is the condition of that area, what is the condition, meteorological condition, or you can say what is the weather system in that particular area whenever we are trying to forecast. So these are the way how the data can be received through telemetric system and keeping it in a database management system like data server. So these are the things we are always little bit anxious and very much interested also. We can go to, these are the some of the methodology that chemical engineering people are using in their analysis. So this is multivariate analysis, online fault detection, inferential sensors, batch data analytics, experimental design approach, parameter simulation, estimation, and model discrimination. Basically, I have gone through some of the literatures of the chemical engineering, and I found that this multivariate analysis is very common. People are using on a regular basis. And what are the molecule structure, how that molecule can be modeled, and what is its composition, how much movement will be there, what is its impact on the total composition of the chemicals. So these are the study and multivariate analysis you can do after collecting all those data, chemical data, I can say. So fault detection, I am not very much sure about this fault detection, how they are doing. But this inferential sensors, I can say you that whatever the sensors they have put on the different scenario, they are collecting the data from the sensors. And experimental design, it is also applicable to our engineering, civil engineering, and other part of mechanical engineering. These are the strategic experimental design approach. Even if in the chemical engineering also, you can make a design, experimental design approach for using this data science. Parameter estimation. Parameter, you may be knowing different parameter, how it is reacting, if at all you are changing somewhere in the composition of the material, in the reaction of the material. Or you can say, if there is some kind of discrimination whenever you are studying the molecular structure of any, or you are synthesizing any molecular structure in a matter or a chemical. And model discrimination, that is also, so whenever you want, there are almost, I can say linear models are very easy to handle. Whenever there is a nonlinear chaotic model, it's very difficult to handle on these parameters. So what you have to do, whenever you are handling this nonlinear model at any field, you can say chemical science or engineering, civil engineering. So you have to be very careful what are the parameters having important role playing in that model. So these are the applications nowadays currently people are using. So issue to be resolved. So these are some of the issues I can tell you that is in data science. Number of publications also discuss organizational and managerial issue. So how to come out with some of the answers that that data science sometimes it is failing. So why it is failing? That you should have domain knowledge. Lack of domain knowledge, lack of trained workforce, lack of clear vision and objective, and it's being viewed as a technical and not a business initiatives. So data science, I can go just a domain knowledge. You have to have domain knowledge whenever you are using any data regarding that domain. And you should have a trained workforce. That means technical workforce. It is talking about technical workforce. Technical workforce means it is the skill. People, those who are getting training, they should have skill how to handle all those data related to that particular domain. And after getting the data, you cannot say that we'll do some garbage thing. You have to have some clear vision how you are going to utilize those data. And out of that, what you are gaining or what you are trying to get it from that data. So clear objective and vision should be there. Otherwise, it is an issue. So it is not a technical and not a business initiative. It is a business initiative. So the thing is, you have to nurture all those data. Whenever you are getting it and whenever you are analyzing it, there must be some business plan, how to utilize it and what is the future predictive model I can make it out of this data. And you should not do data science for the sake of doing data science. There must be some kind of objective and a vision for that. And one more very important thing nowadays, this volume, I can tell you. It's a very difficult to store millions of data on a particular workstation, or you can say data station. So you need to have you have to compose, or you have to make such a way that a big volume of data, it will be organized and it will be stored whenever you want. You can access it from that system. That is called NAS storage, network as a storage. It is whenever required. So making a NAS storage, it is also a big word. And basically I'll talk about our system. Our system now in fourth paradigm institute, we have upgraded it to petaflop machines. That storage capacity, I can tell you, it's a 2 petabyte, petabyte, something like that. They're just upgrading all these things. So these are the lacuna, and these are the issues that should be addressed whenever somebody wanted to do data science. And the technical challenges. The most challenging aspects of volume is that not all data are created equal. You just need analytic skill set to distinguish whether the data are meaningful or not. So whether you are utilizing it, or is it meaningful to you, or it is really need for you to go for this data, it's a very challenging. Then you need a technical, skillful person who can differentiate between what you need it, what you doesn't need it. So he can separate, and this raw data, or you can say not informed data, it is not required, that kind of data. So you can clear all those noise from the real data. And another issue is filter the noise to enhance the signal. So how you can filter? It's a technical thing. Again, somebody has to be a little bit skilled fellow who can realize when information is missing in the data set, and a designer experiment is needed to generate the right data. So you need to generate a right data. Just designing an experiment and producing the data, it won't solve the right purposes. So you have to be very careful whenever you are designing a certain kind of data sets. So real-time data resolution also very important. Wherever you can say the resolution means, I can tell you, the area particularly you are focusing. That maybe I can tell you satellite resolution we are getting now, Modi's data, that is 30-meter resolution and 20-meter resolution. It is available in the public domain. So you need to, as long as you are increasing the resolution, then you are getting a lot of dynamics and a lot of features to be added in the data set. That you have to segregate what is your requirement and how you are going to focus on your required data. That is also an important challenge. And one more thing, how to incorporate all those information or real-time data with the existing models. Suppose I'm running that is a spectrometer that many chemical engineering people they may be using this spectrometer. So how you can incorporate this new information to this spectrometer and finding the data on the right way. So it's applied to without context and domain knowledge. So whenever you are trying to apply all those big data, you have to be very, very careful. These are all technical challenges. 1-2 point, I can again explain here what you need to be done. So for complex industrial process, it is always important the cost, time, and skill required to develop such a fundamental models can be high. From the industrial point of view, whenever you are trying to join yourself or you are trying to make a relation with industries, pharmaceutical science, energy, food, and other chemical sciences, those who are related to particularly industrial corridors, you have to be very careful which way we can save our cost. So for this cost benefit analysis, you can go for either this model and which is a high scientific requirement, I can tell you, and or you need a big data that which can tell you on a applying different statistical analysis, it can predict the future that these are the requirement or these are the structures or these are the things that we really need to implement in our project. So these are very much, I can tell you, it's a fragmented information and very volatile information that you have to concentrate whenever you are going to do the cost, time, and skill analysis in the industrial corridor. So data-driven model can be complement to domain knowledge to generate insight, but integrating fundamental modeling and process knowledge with big data analytics tools to create enterprise scale solution remain another technical challenge. What I told just right now. So lack of an appropriate software platform is an important barrier to overcome, to implement, and to sustain big data analytics application. I'll tell what are the different technical tools people are using the chemical engineering. I have already told in the previous slide some of the techniques and how they're utilizing all this big data. So you need to have an appropriate software also, platform, how you are using it. And these applications require multiple data sources to gather data and also require a fairly complex computational engine to execute their algorithms. How will do it? Some of the complex model you wanted to run in your systems. In that sense, you need a very high precision HPC, high performance computing system in your institute. And what are the application and how you are utilizing it, that is up to your requirement. Suppose you need a computation or you need to run a model. How to do it, how much processor you are using, what is its requirement, how to do the, and basically this biological science people, they're using for this gene sequencing, and particularly in this COVID time, IGIB, there is an institute from CSIR, they're particularly doing this gene sequencing regarding this COVID virus. How these mutants are coming and what are the new variants that may come with mutant and defining the gene from time to time. So these are the very complex issues. Yeah, these are the very complex issues that we have to look at. Whenever we are telling that you need multiple data sources to gather data, that also require a complex computational engine. That's why I'm told different algorithm, how you are going to run it in a different time and space dimensions. So next I can tell you. So variety of challenges in chemical engineering. As I told, these are some of the challenges we face when you are collecting the data. Scalar quantities like temperature, pressure, flow, and concentration. And one-way arrays like spectrum, chromatogram, and particle size distribution scopes. This is one-way array. So I'm telling the different format of data, that how you are going to collect, or you are facing this challenge day by day. Two-way arrays like image and gas chromatography with mass spectrometer. Three-way and higher order arrays such as video and hyperspectral images. So these are the things you are regularly facing in your day-to-day life, how to handle all those data. For that, what you have to do, text data also such as email, operator, logbook, lab notebooks, and social media discussion. So these are the different format of data day by day you are facing in your daily life. But specifically this chemical engineering people, I can tell. So these are two ways, and then it's a very huge amount of data. It's not, I can say this two-way arrays, this chromatography and mass spectrometer data. It's a very huge amount of data. Then how to store it, and what are the tools you need to make an analysis. So these are very, very important things that we have to be careful whenever we are doing this data analysis. So some of the example I can give you. This is just an example I took. So architecture of feed-forward neural networks. Now everybody, I think people are a little bit aware about this artificial intelligence. And these are the basic concept of artificial intelligence, that input layer, hidden layer, and output layer. And this is a radial-based functional network. So what this radial-based functional network is doing, you can see the pattern of data and train your data in such a way that you can able to predict some of the future prediction. That means some of the future aspects, how this data can predict, or it can be used for prediction model. And this is multi-class classification. You can see after using this training data, you can classify all those things in a different varieties of methods are there for classifications of this data. So the typical structure of a feed-forward neural network in this era is shown in this figure we have seen. So it is always easy to handle the linear function data, but nonlinear function approximation and nonlinear classification problem, it's a very tough problem, and you need a lot of data whenever you are talking about this nonlinear classification. So what I mean to say, there are varieties format of data you are using. Even though if you are using this nonlinear data, the amount of data, the volume of data you need to be much more as comparable to linear data whenever you are doing. So this is the automated knowledge extraction framework catalyst design, how you are designing a catalyst. Active learning framework. So you have to do first formulation of experiment, then go to a high throughput experiments, and it will go to reaction modeling suite and chemistry rules you are applying to this reaction modeling suite. And then you can go for performance curves, and after that features extraction, and then go to model refinement. So what I mean to say, these are the learning framework, how you can tune your model. And architecture of reaction modeling suite. So I have taken very recent publication. I think I have forgotten that Journal of Chemical Science. I have taken these figures from that publication. I wanted to just schematic view of this model, how you can really utilize this chemical science whenever you are doing this model work. So again, this chemistry rules you can apply to reaction modeling suite, chemistry compiler, equation generator, parameter optimizer, then statistical analyzer, and then go to the performance curves. How? So these are the processes that we are following on a different stages, that how to handle all these framework catalyst design. Again, I can go. So now I can go to machine learning a little bit. It's a series of computer programs, and its core task is to build mathematical models using statistics to make inferences from samples. I told you. So these are a series of computer programs. Machine learning is a computer programs. How you are training your data, what are the data you are getting, and how you're training with your equation, try to write an algorithm, run it, and then get the output data. A model that defines certain parameters. Learning is the execution of computer program that uses training data or experience to optimize the parameter of the model. And in that sense, whatever you are trying to do it in machine learning, it can predict the future state of the matter, future state of the molecule, how it can be, or what is its role in deciding the future state of the matter. So it's a quotation. Data science has become the fourth approach to scientific discovery, in addition to experimentation, modeling, and competition. So it's a comprehensive approach. It's a experimentation, modeling. Experimentation, how you do? You need data for the experiment. You need data after modeling, how to analyze it, and the competition, how you are going to do it. So I'll skip this thing because it is a lot of time it will take. So I will go for this map function. This is a schematic, totally how you are going to do on the map function. The map reduces the algorithm consists of two primary steps, map and reduce. So in the map reduction, sorted and split between the computing units, different computing units, you have to sort it out. These are the data we have sorted in the different units. Subsequently, so in the reduce step, what we'll do, some aggregation function like mean, maximum, sum. Then after sorting this out, we are trying to reduce the function of all those data that can be sorted it out in a particular format. And reduce function means you are trying to reduce the chaotic movement or chaotic presence of this data on a different. That is some extreme value data will be there. So whenever you are sorting, you are trying to reduce the noise, reduce the extreme value, bias correction, and some of the things like extreme value correction also you are doing in this sorting data. After that, you can get it in a map function. So data engineers Venn diagram. So how decision scientist is the central focus of all these data engineers. So this is just a schematic I wanted to show the people that hacking skills, entrepreneurial capacity, substantive experiments, maths and statistical knowledge. So these are the outer layers. Inner layer, whenever you are entering to the business case development, traditional computational scientists, machine learning engineers, tech moguls. Then again, if you are going inside a little bit, then software developers, then BI developers, data analysts, data scientists. Again, finally, you are going to the decision scientist. So what I mean to say, after all this skill, finally you are reaching in a point where you have to deliver the decision, scientific decision to the society, to the nation, and to the country also. How the community end users they can be benefited from your decision. So these are just a idea I wanted to float it here for some of the people there maybe using the out of this data sources. So just I wanted to give a this is a how you are using a big data, and there are supervised learning and unsupervised learning. So predict classifications or value. These are the two things that it is going to the classification and the regression. how you are doing it? Classification, binary, multi-class, ODL, nominal, then choose the algorithm, then logistic regression, then SBM, then ANN, then decision tree. This is the binary format data. And whenever you are going for the ODL and multi-class data, then you can go to ordered logics model, artificial neural network, and decision tree. And if you are choosing any algorithm kind of data, then multinomial logic model, hierarchical logic model, artificial neural network. So these are the basic schematic what I show. What are the machine learning technique for any big data you are applying in chemical engineering? So this is also just, I tried to understand this is the big data, this is the analytics, and how the decision systems is giving a clarity regarding what to do, what not to do. So these are all about chemical science I talked about. Now I can go for the atmospheric science. If the audience will give me permission, then what are my domain area, what I have done in my career, I can show a little bit, I can explain. Can I go, madam? Hello?
Yes, sir, sure.
Yeah. So, madam, getting bored or any audience getting bored, they can ask me
No.
something. Okay.
Any participants, if you want to ask any question, you can ask. Okay, so you can carry.
Okay. So now the real time how we are using this machine learning technique. So I'm telling you, this is the, you have to first define the problem. Unknown mapping, that is FXY. Then organize the data set. Training set D, that is how you have to train your data. Then set loss and learning algorithm. What are the algorithm you are using? And it is, I think it's a reversible kind of thing. And in the meantime, you can train your data and put it in the algorithm. And what are the hypotheses you are setting here? You are going for search. Then try to find out the learning algorithm and set the optimal parameters. Learn model. Senthil. Little bit. So now learn model and input new data, then prediction system. This is the practical process of machine learning that you are using in the data science. So what are the things I have done here? Collect and organize a training set D with a finite set. Then specify the loss function for the model and select the learning algorithm and obtain the parameters that makes the loss function, fetch the popular hour and choose them as the optimal parameters of the model. Set this model G with the optimal parameters and use it at prediction and analysis of the new data. So these are all, I think this is the basic framework of any machine learning technique whenever you are applying to any data. So I mean to say, if anybody has an interest to go for this machine learning technique, so you can use it as a, I can say it's a schematic, and you can use this kind of techniques step by step to find out the prediction and analysis of any data set. So I can tell you, we have just tried here to forecast a tropical cyclone in my area. What is tropical cyclone? People may be knowing it actually. It comes, though I don't think Bangalore has faced any kind of tropical cyclone, but coastal area, very frequently Indian coast, people like Orissa, Visakhapatnam, Andhra, Chennai, and West Bengal. It's several occasions these people are facing tropical cyclone. Tropical cyclone means there is a wind speed and the rain. They are accumulated and the wind speed is going around more than 120 kilometers or 130 kilometers. We can say it is a tropical cyclone. So how you can predict it? And how you can predict it using the machine learning techniques. So this is my work. I am trying to do it right now on a big project in DST project. So this is a data-driven machine learning model. How you have to find out the different track forecast, intensity forecast, tropical cyclone, weather and disaster impact forecast, genesis forecast, improving the numerical model. After getting all those data, how you are predicting it in a short term, long term, path prediction, prediction mining, and similarity each. And these are the techniques we are using through this machine learning algorithm. So what I mean to say, you can use it in a comprehensive manner to predict short-term and long-term events like tropical cyclone with atmospheric science. And it is proven model. I can tell you, even if we are using this dynamical model, but it is a proven model that this machine learning forecast model, you can do it. It's a comparatively, it is doing also well, not bad, even though people are using the dynamical model. So this is some kind of rainfall data I have used to see over all India how there will be a dry, wet, and a transition phase of a different area in India. So this group 1, group 2, group 3, group 4, and group 5, group 6. These are all group of similar rainfall area of Indian subcontinent, Indian meteorological stations. What I mean to say, group 1 may be containing the central and eastern India. Group 2 may be containing some part of central India and western India. Group 3 may be containing Western Ghat area and some part of the central India. So what I mean to say, or what I wanted to say using this machine learning technique, that after dividing all these groups, this is a cluster analysis. I can tell it is a cluster. Cluster means it's a group of events, group of area, temporal and spatial. Spatial means it's a space-based. Temporal means time-based. So I have taken this data from 117 years data, 16 years data, I can tell you, to do this analysis, and it is published in a very reputed journal, Theoretical and Applied Climatology, and it is a very high impact factor journal with 3.1, I can tell you. So what I mean to say, this kind of analysis can give you the insight that really how that data or big data can play a major role deciding the future prospects or future predictive model, how it can be utilized for our purposes. And I can tell you, these are very, very regressively data used in this model. So you can see all these papers. I can give you a link that you can read this paper. It's a very interesting paper. And this is also the same. It is the work I have done over Bangalore city. This is the steel score of forecast against rainfall categories. So what I have done here, I have categorized all those rainfall events into different rainfall amount. You can see less than equal to 10 millimeter. These are some category, 10 to 20, some category, 20 to 40. This is millimeter, rainfall millimeter. How many events has happened, and what is the model skill to capture all these events. So I found it's a very regressive analysis. I can tell you a lot of data, that model data generated from this our run, that is weather and forecast run we have collected. And after getting all those data, we have gone through rigorous analytics processes of this like what I can say, bias correction and correlation coefficients and relative error analysis. After all these processes, I have found, so these are the success rate, these are the miss, and these are the false alarm sometimes. So no model is perfect. No analysis or predicting model can give a perfection. Then why people will do the research? That I mean to say. So whenever you are doing all this analysis of data, you have to be very, very careful what kind of tools you are using and how it is going to helpful in these tools and what is your intention and objective to do this analysis. This is a model forecast and observation over Karnataka state we have done for this Karnataka state natural disaster management cell. And this is, you can see, this is the 6th July 2021, this 8:30 IST data. And this is our model forecast, how we are doing all this forecast on a real-time basis. So what I mean to say, whenever you are handling all those data on a real-time basis, you have to have a skill how to handle all those data. Why it is looking very, very high resolution? Because you have here 1 kilometer resolution in the model. Even you can see the gram panchayat level also in this model. You can go for the boundary of gram panchayat and you can say where rainfall can happen, where rainfall cannot happen. And obviously, there is a percentage of 70 to 80% accuracy with 10 to 20% error, I can tell you. 20 to 20% error will be there. No model is perfect. Again and again, I'm telling. So whenever we are doing this modeling, we have to be very, very careful regarding the data handling and model analysis. So again, I can go for one more. This is a very, I have published it in Quarterly Journal of Rural Meteorological Society. And this is about the distribution of rainfall over Bangalore city. How we have divided this non-local and local rainfall analysis over Bangalore city. So what we have done here, whenever the rainfall intensity, that is millimeter per day, is above 98% of total number of events, and this is 60 millimeter per day are considered as extreme rainfall events. And this is called extreme rainfall events, more than 60 millimeter, whatever it has happened. So what I mean to say, whenever it is covering more than 95% area, we can say it is a non-local event. And whenever it is covering below 45%, we can say it is a local event. So based on that, we have categorized the distribution of rainfall events in Bangalore city. So it is a very, very, I can tell you, 35 years data we have used here with 0.5 degree, 0.5 degree resolution. And this is from India Meteorological Department, Delhi graded rainfall data we have used it. So these are the applications I'm telling you. Whenever you have the skill to analyze big data, so these are the applications that you can frequently utilize in your research, in your industrial partners, and in your application part. Whatever you are doing, you can contribute to the application part. So these are also same 117 years of data I have used to see the rainfall pattern in different months of all India. So this is the rainfall in millimeter, and you can see there is a patches. Always this patch. January months there is a dry area here. We won't get rain here, and this also we won't get rain here. February also, but just see whenever June started. This is a June map. After reaching this monsoon thing, you can see there is a complete changes of this rainfall pattern, and you can see Western Ghat area, particularly this Maharashtra, Bangalore, some part area is coming, and Kerala coast and Goa. So everything, all these parts are getting rainfall, and this is a 116 years data I have taken from India Meteorological Department. And I found that this is the way how we are really implementing the big data or data science in our research. So it can give you a picture. Suppose why I am doing it, what is the utilization, who is going to be benefited, and how it is relevant. So these are the questions that always we are asking whenever we are doing any kind of research in this area. Suppose why I am doing it. I am doing it for the farmer community. I am doing it for the individuals like farmers, and the I can tell you that marginal farmers, basically those who are depending 100% on the monsoon. From this idea, you can find a trend that this is the rainfall trend, and this much amount of rainfall may happen in future. Based on that, they will put the crop, they will put the paddy, they will put the sugarcane. So this is having real utilization. And you can see again this July, August, September. July, you can see the highest rainfall around 360 millimeters from here. August also here. September little bit in the northeast part, it is shifting. And again, this is a dry phase. It is coming starting from October. You can see that again December it is reaching means there is no rainfall in this part of it. So every data has its own application, own utilization, how you are handling and how you are using it. So this is just that group I told you how I have used the principal component to decide how much in which group, what are the impacts of rainfall at what time. So this is a factorial plane of the principal component of PC1 and PC2 for each special group for determining the variance of rainfall for a period of this 160 years. So this is a very natural thing nowadays. Everybody is asking how you are going to provide or support your research for this readiness level, technology readiness level. So how, whenever you are conceptualizing an experiment and you are doing a fundamental research, then you are in TRL 1 and 2. Then again, you are trying to proof of concept. Suppose you did an experiment or a design and you wanted to proof of concept means you are in the TRL 2, 3 and 4 and you are trying to give it somebody, or you are trying to convince somebody that yeah, I am in the TRL 3, TRL 4. And this technology demonstration, it will come under TRL 5 and TRL 6. Suppose you have the confidence on your technology or in your patent that what I have done that can be transferred or it can be scaled up, then you can go to TRL 7. And commercialization is TRL 8 and TRL 9. So this is the way how we are going to scale up our technology readiness level if at all you are finding any new conventional technology or any kind of technology that we are trying to develop in a large. So from the chemical point of view, chemical engineering point of view, these are some of the papers I have collected, and I found that how much number of journal publications and what are the things that whole world is doing. And it's a very recent publication, I can tell you. So number of AI related journal publication and number of substances associated with each class you can find in the A. So small molecule, element, manual registration, polymer, salt, alloy, ring parameter, inorganic compound, and coordination. All these are number of journal publication and number of substances related to that journal. So they have published it. B also, each substance classes how it has published. So you can find it's the highest small molecule, they are publishing much more in the world level, everywhere they are publishing it. And in the C, you can set each class number of AI related patent publication and number of substances associated with, you can find that AI level, how much each class, how much their publication they're doing. And finally, the publication associated with each substance class, you can say small molecule, element, manual registration, peptide sequence, nucleic acid sequence, and coordination compound, inorganic compound, and leading parent. So these are just, I gave a view of whole world, how they're producing and what are the works that currently going on in different parts of the world. And finally, our India, you can see we are in, always China is surpassing us 26.52% China. And again, the country and the region you can find, this is top 20 countries region in number of journal publication. Again, now USA is going second and India is third. Here also you can find, again, China is first, USA is second, and India is, I think, fifth. Number of organization patent, I think it's very, very less. I think India is not there itself. Top 20 companies in number of patent publications. So India, some company, IBM is there. I don't know, this is a company based, this is not a country based. So you can find these are the latest work that people are doing and they're busy with this kind of work. Finally, how to summarize all these things, I can tell you. So big data analytics is a journey to turn data into insights for more informed business and operational decisions. Again, I'm telling you, all these consequences of big data is coming to operational business. The chemical process industry has been a fertile ground for some of the foundational data-driven modeling workforce. So online instrumentation and centralized control system allowed for aggregation and storage of process data for online monitoring and analysis. And specifically, these pharmaceuticals R&D is incorporating machine learning and dimensionality reduction visualization method to analyze complex data sets such as gene expression, protein interactions, and drug discovery data. So there is a specific, we can call it ODD, drug discovery, and organization of drug discovery. That is a department in Government of India that they're working rigorously on this protein interaction and the drug discovery data. Food industry also, you can see diverse data sources are incorporated in modeling, taste, nutritional content, and recipe formulation for food products. Also, people are using regular basis. The industry is shifting towards using multivariate methods to identify correlation from the bigger data sets. To address the opportunity, academia, industry, and government must collaborate on the workforce and development and analysis innovations. Early adopters need to be established a culture to continuously explore new opportunities and to motivate the rest of the community to start the big data journey. So what I mean to say, as long as quickly if you pick up all these things and you can corroborate within the brain of students community that we have to work on data science, this is the emerging field, and it can help us in the long run. Any domain you choose, but you have to have a specific objective and motivation and a specific direction in which direction you are moving and what you will achieve by moving in this direction. So these are the points that we have to keep in our mind. And finally, I can tell you, a good data scientist is the one who can observe, identify patterns, listen, apply historical knowledge to predict the outcome and tell a compelling story. Thank you everybody for your attention.
Thank you, sir.
Yeah.
Thank you, sir, for your resourceful speech, and definitely the knowledge gained from this session
Yeah.
would be fruitful for our participants.
Yes.
As the professor has elaborated about the data science, artificial intelligence, and he explained the basic difference between the data science and artificial intelligence. What are the application of data science in chemical engineering community? Professor explained and give the detailed note about the technical challenges use big data day by day as chemical engineering and how we can overcome these challenges. Even more, he sir explained the basics of machine learning also, and the data and engineer Venn diagram also explained by sir. Professor elaborated what are the machine learning techniques for big data as chemical engineering, and sir also gave about little bit knowledge about his research area, like how tropical cyclone forecast can be predicted, and about the distribution of rainfall in different categories using machine learning. So thank you once again, sir. Thank you so much. So this is open discussion. So any participants, if you have any questions or any queries, so please ask.
Yeah, you can ask the question. I'm expecting some of the questions.
Yes. Sir, one question is there.
Yeah.
How to overcome 20% of modeling error?
Yeah, madam, that is a, that's why we have got the job here. It's a very challenging question, and that 20% still in NASA and other NCAR, National Center for Atmospheric Research in USA, these people are struggling towards forecasting on this rainfall also. So yeah, so we are searching different, as you told, that the data science technique, how to minimize the optimization technique. What are the optimization technique that you can apply? That at least that bias and this noise kind of thing, whenever coming in the um, experiments and instrumentation that we are correcting, so that can be reduced. I'm unable to answer this kind of question because I'm telling you one example, madam, I'm giving you. Because whenever you are collecting rainfall data, okay, or any data, we should have a proper bias correction process itself whenever you are collecting any data. And in our modeling system, what happens? Suppose you are collecting any rainfall data, the bias was there itself whenever you are giving input to the model. So even this 2% or 3% bias, that will lead to a 7 to 8% bias whenever output is coming from the model. So this is the way that whenever we are collecting any data or we are giving input to any algorithm data science, so this will be a challenging factor that you have to overcome. And you can go for the accuracy level of 85, 90%. And these 10-20%, how you are managing, what are the techniques you are using, what are the experiment you are doing, it's all depend upon the way how you are doing your analysis. That's all I can tell you. And it is very difficult to remove all those 10-15% data, even though we are at the high performance computing, where we are having a very, very high computing system in country and India, also in China, USA, but still we are struggling a little bit. But that's all I can say.
And sir, like we are using machine learning or artificial
Yes.
intelligence.
Yeah,
Which
yeah.
one is good, we can say?
We can say it's depend upon what are the problems you are. Suppose you are doing this event forecast or molecule stabilization technique you are utilizing somewhere. Then you can use this AI for this our model forecast. But in molecule modeling, whenever you are doing, you can use this machine learning. So just collect the data from any instrument, or you are creating data, or you are providing data to your own experiment, and try to do the bias correction in that machine itself, and try to put all those data in the machine learning algorithm. Then you are going closer. You are minimizing the error and going closer to the accuracy level. So that kind of you have to decide whenever you are taking a problem, you can there itself decide which kind of technique I can use, either machine learning or artificial intelligence. It's up to you. And after doing some experiment, you can strongly say that, yes, I have applied this machine learning technique and I got my result. So these are the error percentage you can say whenever you are going to give it to end user person. So these are the, it's depend upon how your problem, it is a very complex issues. It's a dynamic format or in a non-linear position, it's a chaotic position. So you have to decide on that basis. You have to take that technique and you apply on these things.
Thank you, sir. One more question is there. For where we can collect the data for rainfall, and I am interested with air pollutant PM10 and PM25 2.5 data will be available, sir.
Yeah, the pollution control board is there in Delhi. So we have that vast network of collecting this pollution data. That is Pollution Control Board of New Delhi. They have these resources. If you can contact them, then they can give you daily data. I can tell you. Means a daily means a regular data, daily to daily basis data they have. They can provide you some data to do the analysis. That you can do it. Any question regarding this pollution?
Any question? Thank you, sir.
Yeah.
Thank you so much, sir. This is very informative session for us. Thank you once again for accepting our invitation for FDP program. Thank you from the Department of Chemical Engineering. Thank you from the management of MBJ College of Engineering. Thank you so much, sir.
Yeah, so I want to thank you, Bamanagudi sir, and Principal sir, Chairman sir, and all the staffs, specifically this Saki madam, Asuka madam, and other people, those who are involved in this FDP program. So it is a really eye-opener program that the participants, they can learn many things from this thing. And it is a kind of network connection. It will go on and on and on. I hope so. People may have enjoyed my talk. Thank you, madam. Thank you.
Thank you so much, sir.
Thank you, sir. Thank you, sir. Thank you, sir. On behalf of MBJ Chemical Engineering Department and on behalf of MBJ CE, I'm extending my sincere thank you for you, sir. Thank you for your valuable time, sir. Thank you so much.
Okay, madam. Okay. Thank you.
The participants, next session will start at 2 o'clock. Feedbacks form will be the next session will start at 2 o'clock. Dr. Kundri Aditya sir, Assistant Professor, Department of Computation and Data Science, ISC Bangalore. Please join before 10 minutes. Feedback link will be uploaded here in chat box. Afternoon, sir.
Good afternoon.
Sir, if you want to check your presentation, you can.
Sure, I'll check. Do you see my screen?
It is visible.
Okay.
We can wait for sir just 5 minutes as participants are joining.
Okay, sure.
Okay. Sir.
Do you want me to unshare or?
Yes, sir.
Yeah.
We are getting. Yes. Good afternoon, sir.
Good afternoon.
Start. Rise, awake, and stop not until the goal is reached. With this inspired quote by the Swami Vivekananda, I would like to start this session. I am Sakshi, Assistant Professor of Department Chemical Engineering, MVJ College of Engineering. Good afternoon to all. My sincere greeting to all the participants who has joined with us in third day of 9th session of 1 week online FDP program sponsored by AICT training and learning on data science and artificial intelligence in chemical engineering, recent trends and future outlook, organized by MVJ College of Engineering, Department of Chemical Engineering in association with IIC and IQASC. Today, we have most eminent resource person, Dr. Kundri Aditya sir, Assistant Professor, Department of Computational and Data Science, ISC Bangalore, with us. Let me highlight the key credential of his achievements. Professor has completed his PG from Georgia Institute of Technology and PhD from Texas A&M University. Sir has very good research publication in international journals. The professor has established his research interest in the area of numerical methods, high performance computing, data science, and scientific machine learning. With this short note, I would like to invite Dr. Kondra Aditya sir to deliver his speech. Sir, you can take that.
Thank you very much, Dr. Batra. Thanks for the welcome. I would like to thank Professor Atira Ashokan and Dr. Manisha Bal for inviting me for this event. So I'm Aditya. Let me share my screen first.
Yes, sir.
Okay, so you're able to see my screen?
Yes, sir.
Okay, yes. So I have joined IISc about 2.5 years ago, and I work at the intersection of fluid mechanics, high performance computing, and machine learning. So in this talk, I'll highlight on how we can use machine learning to accelerate these high precision, high fidelity numerical simulations to understand reacting flows. In particular, what I would focus on is reacting flows applied to combustion. And here we look at two aspects. One is engine combustion for energy application, and one more is engine application in scramjet engines for hypersonic flight. So before I start, I would like to make a brief acknowledgement. I would like to acknowledge my student Shubham Kulkarni and my collaborators at Sandia National Lab, Hemant Kola and Jacqueline Chen. So here is a brief outline of today's presentation. I'll start with an introduction about the lab that I have established at Indian Institute of Science. It's the FLAME lab. Then I'll give you a brief introduction about scientific computing, some of the key challenges as we move towards the next generation of supercomputers. Then I'll highlight two applications which would use simulations on really large supercomputers to understand some of the key fundamental reacting flow physics. And once we establish that, I will pose some challenges and get into the machine learning aspects. Here I have chosen to elaborate on two specific topics. One is called anomaly detection. The second is called super resolution. I'll be mentioning the application of these two in simulation workflows and then provide a couple of examples. Finally, I'll end the presentation with some brief conclusions. So I want to make this session interactive. So if you have any questions, please feel free to stop me and then I'll be happy to answer the questions. Let me see if I can also bring up the chat here.
The chat box is there.
Yes, I just need to bring that up. Yes. Okay. So either you can unmute yourself and speak up, or you can post a question in the chat. I'll be happy to answer.
Okay, sir. If
Okay.
anybody has question, they can ask.
Yes. Thank you. Okay, so after I joined IISc at the Department of Computational and Data Sciences, I have established this lab called FLAME Lab. FLAME stands for Flow Analysis and Multi-Scale Physics Simulations at Extreme Scale. So what we do is, in terms of science, we work at the intersection of flow physics. To understand flow physics, we want to employ numerical methods and perform simulations. And these simulations are really very expensive. So we want to use parallel computing and supercomputers to perform these simulations. And once we perform these simulations, the data that we receive is really large. So from one big simulation that we perform, the data is of the order of 25 terabytes. So we cannot even store them on small computers or laptops. It's also difficult to have such a huge RAM to load all the data and process it. So what we have to do is we have to again look at HPC methods to perform data analysis. And here we want to use machine learning to accelerate the analysis aspects. So this is in terms of science. So we work at the intersection of all these three circles. So when we work on these things, we have established a simulation workflow. Okay. So here what we work on is first thing called high performance computing centric numerical methods. So for example, if you take any differential equation, you know that there are several methods to solve each of these equations, right? But not all the methods are scalable. By scalable, I mean that they are not amenable to perform simulations on a supercomputer. Okay, I'll be talking more about the scalability aspects a little later. Second thing is, so now what we want to do is we want to either identify the existing methods that are scalable or that are amenable for HPC platforms, or we want to develop new methods that are suited for the supercomputers. So once we have these numerical methods, we want to discretize the governing flow equations and then integrate them into a simulation workflow that we want to perform the simulation on. The second aspect is to introduce scientific machine learning aspects. So here we can use machine learning in different areas. The first one would be what we will discuss later in terms of dimensionality reduction, or it can be using machine learning methods to have turbulence closure models, or we can use them for reducing the amount of data that we generate from these simulations. So combining the research in these three aspects, we want to put together, and what we will obtain is a multi-scale multi-physics flow solver. And we want to use this solver to understand some of the key problems in turbulent flow physics. Specifically, we want to look at three applications. The first one is combustion. The second one is high-speed aerodynamics. The third one is related to pollution and environmental flows. So now I'll move on to providing a brief introduction about scientific computing. So here I'm showing you a picture that has different applications, right? The first one, aerodynamics. Then you want to look at some material properties in material science, drug delivery, specifically with COVID and other things. There's a lot of emphasis on performing simulations to come up with new drugs that can bind with these virus, right? And then these are also extensively used in oil and gas industry, where a lot of these chemical processes are simulated. In terms of weather, as you are aware, right, our daily weather is obtained from various massively parallel simulations. And then whatever we want to propel in terms of aircraft or rockets or something, we want to perform simulations and understand the key physics. So these are several applications where scientific computing is being used to understand some of the key physics and to develop the latest technologies. So in our lab, what we work on is in terms of either aerodynamics or in terms of propulsion. These are the two specific aspects that we perform simulations on in our FLAME lab. So now let me give you a brief overview on the workflow that is used in scientific computing. Here on the top, you see an image of a turbulent flow. This probably looks like something like a fire, but as you see here, this is an image that was generated from a computer simulation. So this is not a picture of a real phenomena, but we have simulated that phenomena like a digital twin. And then we visualize that, and you see the kind of structure that is available here. So you see that there is a really large scale. And then within this large scale, there are smaller and smaller scales. So this is what is referred to as a multi-scale phenomena. And this is very common to turbulent flows, as you are aware of. The second thing is the simulations that are used in weather, where we want to understand the rainfall, we want to understand the temperature distribution, humidity, etc. The last two are the simulations that we have performed in our lab. These are, the first one is a simulation of a scramjet engine. The second one is a simulation of a gas turbine engine. I'll show you these two examples in a bit more detail in the later parts of the slide. So in generating all of these things, there is a single principle that converts the governing equations and perform simulations and generate the data. We will look at what that workflow is. So the governing equations here are the conservation of mass, momentum, energy, and species, right? We take these governing equations, which are partial differential equations, and we use any method like finite difference or finite volume or finite element, any of the PDE methods, and translate those partial differential equations into algebraic equations. Once we have them in the algebraic form, we can write a code either in C, C++, or any of these standard compile languages, and then perform simulations on any either desktop for a small scale simulation. But as complexity of these flows increase, we need to have larger computing power. This is established through smaller clusters or servers. And eventually what we do in our lab is to use some of the top supercomputers in the world, where we run a simulation on roughly around, I would say 1 lakh to 20 lakh processors per simulation. Okay, so when we run such a large simulation, we generate lots of data. And finally, what we do is we perform data analysis from the simulated data and understand some of the key aspects of the flow. How does the reactions happen in the flow? How does the chemistry or the chemical reactions interact with the flow dynamics? So these are some of the aspects. So now with supercomputers, sorry, some issue. So here I'm showing you a picture of two different supercomputers. The first one is at IISc. This is at the Supercomputer Education Research Center. This is supercomputer has about 40,000 processors, about 50 GPUs. The next one is a supercomputer at the Indian Institute of Tropical Meteorology, Pune. These are some of the top supercomputers in India. And we also have access to 2 or 3 top supercomputers in the world to perform our benchmark simulations. So this is what I refer to as HPC, High Performance Computing Platform. And with this, and along with machine learning and AI, we want to integrate these two computing technologies into our simulation workflow. So what happens with HPC? I depict this with this arrow here. So with the amount of HPC supercomputing power that we have, we can now perform simulations on really large grid sizes. Or if you take a particular problem, we can simulate the problems with more amount of complexity. So for example, if you are performing a combustion simulation, it's not just the pressure, temperature, or the velocity that we want to get. We also want to get the detailed chemical composition of the flow at different points, right? Where do we have the fuel components? Where do we have the intermediate species? Where do we have the products of combustion? So we want to get all of those things in a detail on a really large mesh. So currently we are able to simulate meshes of the size of billions of grid points on these supercomputers. Once we perform these simulations and gather the data is typically very large in terms of volume. Currently, one of the simulation that you are seeing here, we have generated about 25 terabytes from a single simulation. And this simulation has run for about 20 days on around 1 lakh processors. So about 25 terabytes of data, we cannot imagine loading them on any desktop or high-end workstation, but we need to perform the simulation on a distributed platform like a cluster or a server. So now what we want to do is, because the data volume is really large, we want to use, obviously one person or a single research group cannot look at this data in its entirety. So what we want to do is we want to employ machine learning or artificial intelligence techniques to identify some of the key patterns in the data and give those patterns and the information from the patterns to the application scientist. and the scientist can look at this reduced volume of data or the specific locations in the data and perform further analysis. So what we want to do is we want to use machine learning to aid the simulation workflow process. So how does that interact? So here, first thing that we want to do is in terms of data analysis, we want to employ machine learning to detect patterns or to detect anomalies. So by here anomalies, I mean these are the parts of data where the phenomena that is occurring in those locations is significantly different from the background. So for example, if you have a box filled with fuel and air, if a small ignition kernel occurs or if a small flame occurs, that flame region is different with respect to the background and it can be labeled as an anomaly. So what we want to detect is if you are interested in understanding the burning aspects of the flame, we can only analyze the data in this specific region and then perform the further analysis. For that, we need to identify where exactly the flame is happening. So we want to use these anomaly detection methods. And as I was mentioning earlier, we can also use machine learning to create subgrid models. For example, if you are aware of these simulation techniques in fluid flow, we have the very high fidelity, high resolution simulation, which is the direct numerical simulation. If we cannot afford direct numerical simulation, we can look at what are called large eddy simulations. LES, and the next paradigm is the one that is often used in industry. It is called Reynolds average Navier-Stokes equation. So as you go from DNS to RANS, the accuracy of the simulation decreases. However, what you can do is you can run the simulation at a very cheaper cost. For example, the DNS can be run only on big supercomputers, while a RANS can be run on a desktop or a laptop. However, for RANs to provide an accurate solution or a reasonably accurate solution, you need to create what are called the subgrid models or the Reynolds stress terms. So these are being developed based on machine learning methods in the current trend. Okay, so these are some of the applications of machine learning in this workflow. Now we want to again we are not just interested in developing these machine learning methods, but these methods have to work on a supercomputer. That means these methods should be scalable. So that again interacts with the machine learning interacts with HPC in a distributed data fashion. Okay, so this completes the simulation workflow for scientific computing. Just to summarize here, we start with a set of governing equations. These are usually the conservation equations of mass, momentum, energy, and species. We discretize these partial differential equations using finite difference or any of the PDE techniques. Once we have that, we develop a code that solves these algebraic equations. We perform simulations. We gather large volumes of data. These simulations are currently being performed on really large supercomputers, and they generate lots and lots of data. What we want to do is we want to use machine learning either to reduce the data, aid us in performing data analysis, or accelerate some of these simulations. Okay, so what we are interested in is in the simulation workflow, the scalability aspect, the HPC aspect, and the machine learning AI aspect. So now let us look at a brief introduction on turbulent flow simulations. So here are the governing equations that we use to perform our simulations. Here we have written these equations in a compressible reacting flow format. So here the first one is law of the conservation of momentum mass equation, right? So this is a time dependent partial differential equation where you have the time derivative on the left hand side and the spatial derivatives are on the right hand side. Likewise, you also have the momentum equation, which has three components in 3D simulation, the X, Y, and Z components. And then you have the energy and species equations. Here, if you see on the right hand side, these are all complicated terms that are combinations of either divergence of some fields or gradients of some of the fields or the Laplacian operator, right, which depict the advection, diffusion, and the reaction processes that are involved in any of these equations. So if you see, these are, as you see here, these look like four equations, but in general, the mass equation has a single scalar, which is the density. The momentum equation has three scalars, which are the three components of velocity. The energy E has a single scalar, but the species equation that you have here can be as low as something like 3 or 4 and can be as high as 100 or 200 variables. So that means for each chemical species that you track in your reacting flow, we need to solve the governing equation for species conservation for that particular component. For example, if I take a simple reaction that I would show in the next slide, like H2 plus O2 gives water, right? So this is simple one-step chemistry for hydrogen combustion. Here we have three chemical species, H2, O2, and H2O. In this case, you have to consider three different species equations that will add to the amount of computational complexity, right, in our simulation. So now in general, as you are all aware, right, in terms of chemical engineering, whenever you have H2 and O2, right, molecules colliding, H2O does not form instantaneously. It has to go through several intermediate steps, which are listed below. So for example, the hydrogen molecule will collide with oxygen and generate something like an HO2. The HO2 in turn reacts with or collides with oxygen atom and forms O2 and OH. So there are a series of reactions, and then there are several intermediate species that form when you have a hydrogen combustion that takes hydrogen and oxygen from air and reacts to form water. So what we do in this direct numerical simulations is to consider all of these species and all of these chemical reactions in performing our simulations so that we precisely know which chemical state we are in at different spatial locations as well as in time. So considering this amount of complexity, right, with where we solve all the governing equations and then consider all the chemical species, the simulations are going to be expensive. So when I come to simulation, I want to give you a brief introduction here. In most of the combustion simulations, the flow is turbulent. That means it is going to have a multi-scale structure. In order to resolve all of these structures, we need to perform what are called the direct numerical simulations. These simulations resolve all the scales or to precisely mention all the dynamically relevant scales, both in time as well as space. Let's consider L to be our large scale and eta to be our Kolmogorov scale. We know the Reynolds number can be defined as the ratio of the scale separation. And this is what is the expression that you have here, right? Then this, if you look at this Reynolds number, it is typically very high for practical applications. For example, if you consider any reacting flow in any of your process industry workflows, right, they often are not laminar. They are always turbulent, and those simulations are because of the multi-scale nature are very expensive. For example, if you consider the computational effort C to perform one particular simulation, it scales as Reynolds number power 3. That means every time you double the Reynolds number, your computational effort goes by 8 times. Okay, so this is the reason why we cannot perform these kind of simulations on simple desktops. And what we need are these parallel computers. Okay, so now here I'll give you a brief introduction about parallel computing. So here we follow a particular setup called the distributed memory or the domain decomposition setup. For example, to illustrate this, I have this picture here. I have a domain which is like a rectangle, and I want to simulate the flow in this rectangular box. Okay, so here let's say that we have flow that is coming in from left and exiting this box from the right. Let's say t is the amount of time that it takes to perform the simulation. Right. So now what we want to do is we want to reduce this simulation time. We say that, okay, my laptop or my desktop has two processors or two cores. I'm going to decompose this domain into two halves. The first half is given to the first processor or the first core. The second part is given to the second processor or the second core. So now each of these processors will independently compute these subdomains, right? And then provide the solution. However, while computing, you need to exchange some information between the two subdomains. This is typically occurring due to the computation of gradients and spatial derivatives. So what we have is the computing time goes by T over 2 because we have two processes. That computing time becomes half. However, we need to exchange the information, and hence we have the additional overhead, which is this plus C2 term that corresponds to the communication between the two processors. Okay. Likewise, if you consider a simulation with 4 processors, the whole domain is divided into 4 parts. And now you have each of these processors or cores computing each of these smaller subdomains. Obviously, the computing time will go by T over 4. However, the communication between the different processors is now increased, and you will have an additional overhead of C4. Okay, so if you want to come up, understand this scaling, if P is the total number of processors that we have and C is the amount of computational effort that we need to use to get the simulation done, the time to compute the solution scales as C over P. So that means as you increase the number of processors, the computing time decreases. And this is called the ideal scaling law. And I'll now plot a graph that depicts this scaling. So here in this XY graph, on the x-axis, I increase the number of processors. Here I am performing a simulation of isotropic turbulence at a grid size of 10 to the power of 24, around 1 million grid points or 1024 cube. So this was done on a supercomputer at Oak Ridge National Lab. And on the y-axis, we are measuring the time taken to compute one time step in our simulation. So ideally, if you keep the computational effort to be constant, which is what we are doing, we are keeping the grid size to be 1024 cube. What would happen is the computing time should go as this law, right? This is an inverse law, which is depicted by this dashed line. So this is a linear scaling line with a slope of -1 that comes from this ideal scaling law. But what happens in actual practical simulations is that things deviate from this ideal scaling law, and you start seeing these gaps between the ideal scaling and what we actually measure. These stars are what we measure from the simulation, and these are the times, or these are the overheads that are because of the communication or the information exchange between different processors. So these are the communication overheads. And now what you see is that at one point, the amount of communication time between different processors would be comparable to the computing time. Okay, compute is what we are really interested. But in order to compute in a parallel computing supercomputer, we need to exchange information. If the communication time is really large, then there is no point in running this in parallel, right? So this is what we mean by scalability. If your code is scalable, these blue timings, C2, C4, or this communication overheads should be really small, okay, when compared to the computing time. However, as you see, as we move to a really large number of processors on these big supercomputers, this communication time becomes more and more overwhelming. Okay, so what we work on in our lab are to look at HPC centric numerical methods that would allow us to bring these stars closer to this dashed line. Okay, so I'm not going to discuss this because we are interested more in data science in this talk. Okay, but if you are interested, you can just send an email and I'll be happy to reply. Now let us look at what has been done in terms of these big simulations over several decades in the past. Okay, here we consider simulations of turbulent combustion, which are reacting flow dynamics, and we consider a code called S3D, which is one of the well-known codes in the world for combustion. Specifically, we are looking at direct numerical simulations. Here I show you an XY plot where on the x-axis I report the year when the simulation was performed. On the y-axis we show the problem size, which is in terms of the number of grid points. So S3D is around 20-25 year old code where the first simulation was performed in a single 2D domain where you have just the flow, right? There are no chemistry, nothing. At that time, supercomputers are capable only to perform these flow simulations based on direct numerical simulation technique. As we evolved later in early 2000s, we were able to simulate 2D simulations with global step chemistry. That means if you consider our earlier example of hydrogen combustion, where H2 plus O2 gives H2O, right? We were able to do those single step reactions with flow dynamics in early 2000s. When you move to the late part of 2000s, right, closer to 2010, we were now able to, with the evolution of supercomputers, we were now able to perform simulations that are three-dimensional in nature. So that means we will get all the three components of velocity in space, and we were able to not relax the limitation of single step chemistry. That means you can now go with detailed chemistry, which involves a lot of these intermediate species. And here we are looking at a reacting system that would contain about 20 chemical species and maybe about 100 reactions. Okay, so that is what we could simulate on these big supercomputers. Later in early around 2011, 2012, we were able to increase the simulation size by increasing the number of chemical species that we track, somewhere from 20 to now we are able to go up to 100 species, right? And we are also now able to simulate perform simulations at really large pressures that are relevant to practical engines, right? And recently, my group has performed this big simulation where you see that instead of just a single box, we are now able to put different boxes like Legos and construct these complex geometries that are relevant to industry and perform a direct numerical simulation. So this simulation, if you see, has about billion grid points, and the simulation was performed on about 1 lakh processors for about 20 days, right, to get the solution. So this is what we refer to as simulation at scale. So at any given time in our evolution, right, the simulations are of a certain power. Based on the power of those supercomputers, we are able to increase the complexity of the reacting flow systems that we can perform. And as we are evolving, currently we are now able to do simulations that are relevant to practical engines in either application of energy or aerospace or transportation, any of these sectors. Okay, so now I'll briefly touch upon the next generation of computing platforms. These are called exascale supercomputers. So what is an exascale supercomputer? It is a supercomputer that would have about millions of processing elements. These processing elements can be CPUs, GPUs, or the latest technology, which are the FPGAs. What is their capability? These supercomputers are capable or will be capable of performing 10 to the power of 18 floating point operations based on double precisions, or 10 to the power of 18 flops per second. Okay, so that is the amount of computing power that would be available on these big supercomputers. And these computers will have about millions of these processing elements. They can be CPUs, GPUs, or FPGAs. And what is the amount of power that we consume on these big supercomputers? The supercomputer consumes about 40 megawatts of power. This is like powering a mid-sized city in India, right? So 40 megawatts of power is not something trivial. It is it can power something like Tirupati or something like Bhopal in its entirety. So that means this supercomputer eats up lots of power, and we need to use it wisely in a scalable fashion or efficiently to get the key insights into the physics. That is what we will be interested, and I'll be elaborating how we can use machine learning to look at these simulations. So some of the issues in the future computer are there will be millions of processing elements which will be connected by these network cables, something like your LAN cable, and these will become very complex, right? Imagine connecting million processors. So this will involve large number of communication affecting the scalability of these reacting flow solvers. And in addition to that, there will be an issue called performance variations, because not all the processors will work at the same speed. Some might have cooling issues, some might have some memory issues, all of these things happening, right? So we have to understand how to work in an environment that is not uniform, where you are expected to get into performance variations. Then the other two aspects are synchronizations and system faults. I'll not get into these, but these are some of the issues that we want to address. And traditionally, we want to address this at a software level, but with the availability of machine learning, we want to see whether we can address some of these issues using machine learning or AI techniques. So the parameter to compute in a scalable fashion are the data is massive, right? The computations are again going to be massive. The scalability is important. And once you have a scaled code and perform the simulation, you are going to generate lots and lots of or large volumes of data. Okay. So what are the solutions? We want to accelerate these computations so that we don't waste too much of power. We want to do this by performing dimensionality reduction. I'll touch upon this topic towards the end. The second aspect is parameter estimation. For example, there are in industry you are trying to optimize, right, as a reaction process, right? You want to sample the data at different conditions and then estimate what is the optimal parameter. So can we use machine learning and AI in parameter estimation? The next one, I apologize for the spelling mistake here, is in terms of data analysis. As you see, the data would be of the order of tera and petabytes, and we want to use machine learning and AI to perform data analysis and come up with or discover new physics that comes from the simulations. So here I want to briefly discuss about two applications. The first application is relevant to hypersonic vehicles. So hypersonic vehicles are the next generation vehicles which fly at a speed that is 5 times, a minimum of 5 times the speed of sound. Okay, so that means you can travel maybe from Bangalore to Delhi in maybe less than like in half an hour or so, right? So that is the kind of speed that we are looking at. So what is the difficulty here? One of the key challenges in developing a hypersonic vehicle is the combustion that happens in this vehicle. These are called scramjet engines. So to give you a flavor of how difficult it is to combust the fuel and air, let me give you a simple example. Let's say that I have a room and I place a candle in the room. I have a matchstick. I can just light the matchstick and light the candle, right? So it's then the candle will keep burning the wax. Now imagine, right? I give you the same experiment, but now I turn on the fan. Right? It is isn't it difficult now to light the matchstick? The answer is yes. Right. So what do? We typically put ask one of our friends to come over and then put a hand around the candle, right? And then we light the matchstick and then do it. So what are our hands doing there? Our hands are creating a disturbance-free zone such that the candle can light and the flame can sustain. So that is a challenge that we have with a simple flow that is created by the fan. Now imagine a scramjet engine where the flow here comes at around twice the speed of sound. So you can imagine, right? This will be around 7 to 800 meter per second velocity. All right. So with that velocity, it is very difficult to stabilize the flame here. So what they typically use are these flame anchoring mechanisms or flame holding devices. One of the examples is a cavity-based stabilization, where you have the radicals of the simulation or the process that are trapped in this cavity, and they provide the necessary enthalpy and radicals to have a sustained combustion. Excuse me. To have a sustained combustion. So now on the right, I'm showing a picture of one of the experiments that was done by our collaborators. Here you see that the flame is anchored at the tip of the cavity, and then you have a combustion happening in this bright region. So these were experimental techniques. As you see here, from experiments, what you can measure is mainly this intensity of the image, right? That gives us some information about either the temperature or the concentration, but you do not get the entire information, right? I want to understand what is the exact chemical state that you cannot measure from experiments. So what we do is we perform simulations of similar setups and get a detailed analysis on the chemical pathways. So here I give you a picture of the simulation that we have performed. So this was performed on a grid of 2 billion grid point size. This was performed on 90,000 processors for about a month. And the key interest here is to understand the flame stabilization mechanism at very lean combustion conditions. And what you see here is a cavity engine where the reactants are coming from the left, the products are going to the right. What you see, these orangish regions are the reactions where you have heat release, right? That they are the flame. The contours in the gray scale are the representative of temperature. So the temperature is very light here. And after the combustion, after these orange regions, the temperature contours have become black, showing that the products are at a much higher temperature than the reactants. So this is because of the exothermicity involved in that process, right? So currently we are writing this up for a manuscript, and these results are key for developing some of the concepts in hypersonic combustion or scramjet combustion. The second application is towards energy sector. Here what we want to achieve is a zero emissions energy system, right? So what does the energy system contain? The first thing that we have at the source is generation of energy, right? With low emissions or zero emissions, we are interested in renewables. So for example, here we consider wind and solar. Not every day is a windy day and not every day is a sunny day, right? So in those case scenarios where you don't have sufficient energy coming from renewable energy sources, we want to supplement the energy requirements by burning either fossil fuels or fuels from other sources like hydrogen combustion or biogas. The overall goal is that on any given day, we should be able to provide a stable grid or a stable transmission of electricity for the consumption in a particular city or in a country. Okay. So now let's look at a scenario where we want to burn these fuels in a gas turbine engine in a power station, right? And why do we need this? Because we have renewables. But as I was saying, not every day is a sunny day or every day is a windy day. So what we want to do here is we want to consider the electricity that comes from really windy days or really sunny days and use electrolysis to convert water into hydrogen, right? This hydrogen can be stored and then again burnt in a gas turbine engine for power generation, and this can provide power when you don't have enough energy coming from the renewable sources. That is the way we want to have a balance between different energy sources and then get a stable power generation system. In this aspect, we are performing simulations of one particular engine, which is called the reheat gas turbine engine. This engine is a trademark, or it was developed by an Italian company called Ansaldo. This is a H-class gas turbine engine. It's called GT36. This gas turbine engine has two combustors. The first one is a first stage combustion that is stabilized, or where the flame is stabilized using typical or common bluff body or swirl stabilized flames. The second stage is where the products from the first stage come in. These are at really high temperatures, so the flame would stabilize using an auto ignition process or spontaneous ignition process. What we are interested here is to look at the detailed analysis of the burning that is happening in this box, so that we can understand in achieving the required goals or required combustion characteristics in our engine design. Okay, not all the operating conditions will lead to an efficient combustion or will lead to low emissions. So our aim is to identify the combustion processes that will lead to high efficiency, low emissions, and fuel flexibility. So we have performed a big simulation using about 1.25 billion grid points on about 50,000 processors. And we have what I show here are the contours of vorticity that are present in the flow. These are colored by temperature, that is going from blue scale to red scale. Blue means you are in the lower temperature region, which is typical of the reactants of combustion. The red regions or these orangish regions are where you have the products of combustion that are at higher temperature. The red region that you see here is the flame that is sitting in the combustion chamber. Okay. So this simulation I want to emphasize because we have performed a detailed machine learning based analysis to look at the aspects of combustion for a situation like this. So what you see here is the engine has two parts. The first one is called a mixing duct, which mixes the fuel and air and also provides the necessary residence time for the fuel air mixture to auto ignite or to spontaneously combust in the combustion chamber, which is the second half. In the combustion chamber, you have the reactants coming from the left, you have the flame, and in the flame, the reactants burn, and you have the products of combustion, which are on the right side. These are at a hotter temperature. That will allow us to expand the gas turbine and generate the necessary electricity. Okay. So these are the two examples that we typically work on in our lab, and we use direct numerical simulations to understand these flow aspects or the chemical processes. In the next 1 hour, I want to emphasize on two machine learning techniques, how we are going to employ those to these simulations and understand some of the key aspects. Okay. At this point, I want to take a break for about 5 minutes. I'll be happy to take questions, and if not, we can proceed further after 5 minutes.
Yes,
Any
sir.
questions?
Any participants have any question? Can raise your hand. No question, sir. Means
Okay.
can wait, or if you want to continue, then we can continue.
Yeah, maybe I can. I'll just go ahead and continue. I'm okay with it. That's okay, right? I can go ahead and continue.
It's okay, sir.
Yeah. Okay. So now let's look into the machine learning aspect of how we can use different methods. Specifically, I'll be showing you one method that we have developed in our lab for anomaly detection, and then I'll talk about a new technique called super resolution technique that is very typical of any images, especially on our phones, Android or iPhones. How we can use such a method in performing chemistry relevant simulations. Okay. So if I go back to this earlier simulation of this reheat gas turbine engine, the simulation or the combustion is supposed to happen in the combustion chamber. But if there are some pressure oscillations in the engine, what would happen is you will have premature or early auto ignition of the fuel and air. So your flame is supposed to be established in the combustion chamber. However, because of some pressure oscillations, you will have burning of the fuel and air happening much earlier, ahead of the flame. What would this result in? This would result in poor combustion characteristics and often might also result in failure of the engine itself. Okay, so we don't want to get into such a situation. So if you now consider this process where you have this early auto ignition, this is an anomalous or an extreme event. What is the normal event? Normal event is where the reactions are happening mainly in the combustion chamber. However, whenever you have these pressure oscillations, you have some abnormality or an anomaly. This results in this early or premature auto ignition, and this is an extreme event that might lead to poor performance of the engine or the failure of the engine all by itself. Right? So what we want to do is we want to understand what are the reasons for the formation of these anomalous events. Can we use any machine learning technique to detect these kind of events, right? And understand the inception of these events, right? Why are these events happening? Similar applications can also be found in other applications. For example, in weather, you have these cyclones that are forming. These cyclones can have catastrophic damages, right? That can be either economic or in terms of humans, right? So what we want to do is we want to predict these cyclones at their inception so that we can send alerts to the necessary locations where we can do evacuations or take the necessary measures. Similar thing can also be looked at in terms of material properties, right? You want to have materials that are where we want to understand the failure of materials, right? So for example, if you have some dislocation in a material, right, this dislocation can quickly under extreme conditions of stress or in terms of force that is applied on the material, it can lead to these cracks and then eventually resulting in a failure of the material itself, right? So what we want to do in all of these cases is use any machine learning method to detect the inception of these extreme or anomalous events, and then understand the reasons why these are occurring. So now I want to briefly discuss about the applications and also the data that comes out from these simulations or experiments, right? So for example, machine learning is now widely being used in many uh, uh, social networking applications, or in terms of e-commerce, where Amazon will recommend what you want to buy next, or Netflix will tell you what movie you want to watch next. So they are being widely used very successfully, I would say, in all of these scenarios. So now, how do those methods translate towards scientific applications, like what we are looking at here in reacting flows, right? So how do we get data from for these scientific phenomena? We either do perform experiments or observations where the data comes from either images or sensors, or we perform a detailed simulations as I explained earlier, and where we have large volumes of data, right? So these are the sources of data. And now what we want to do in terms of analysis using machine learning, we want to predict or forecast these extreme events. In particular, we probably want to say, right, the extreme event is going to occur at this particular time or in this spatial location. So can we come up with a granularity in terms of prediction? And in doing so, we want to use both supervised methods or unsupervised machine learning methods. I assume that you already had a lecture on the basics of machine learning in AI that were covered in other lectures of this FDP program. Okay, so now in this slide, I want to briefly talk about the attributes of scientific data. Right, scientific data is different from the data that we collect in social networking settings. Right, so in social networking settings, for example, if you consider fraud detection of any credit card transaction, what would you collect? You would collect the time of transaction, the location of the transaction, right, and the amount of transaction. So all these are very discrete kind of data, right, and they don't have any structure or pattern possibly. However, scientific data, right, is usually multivariate in nature. For example, in the reacting flow simulations that we would consider, we would track anywhere from 9 to 100 parameters, right, 100 variables. So it is multivariate in nature. And the flow that we observe is also multi-scale. That means there are highly nonlinear terms, which in practical applications result in multiple scales. And we want to resolve all of these scales, right? And we perform these DNS simulations. So the data has by a construction a multi-scale nature. And then when we do these high fidelity simulations, or when we use these supercomputers, we are able to now resolve all this multi-scale data in a very smooth fashion. That means whenever you have any abnormality, the abnormality will not show up as a single spike in the data, but a several grid point data will represent an anomaly. That means what I want to mention here is that the anomalies that you see here are not point anomalies. That means if you see a recording at a particular location, you cannot say whether that point is anomalous or not. Only when you look at a data in a particular location and analyze that, then only you will be able to mention whether it is anomalous or not. So that is because it comes from the smoothly varying nature of the variables that we have. And when we perform these simulations, we do transient or time dependent simulations, or when you perform experiments, you want to see how the reactions evolve in time, right? So the data that we acquire will also stream in terms of time. So the anomaly is not just in spatial location, but it can also happen within a time window. The next aspect is the data that we generate is massive. It can be either both in terms of experiments, where you have now sophisticated measurement techniques or sophisticated sensors, or in terms of computations, where we are generating terabytes of data from these big supercomputer simulations. So the bottom line here is that we need an intelligent workflow to compute, analyze, and store data. So can we have a machine learning or AI solution for achieving this goal? So in doing that, first thing that we want to focus, or that we have been working on, are these anomalous events. Anomalous events are something that are characterized by extreme values in the joint distribution. That means when we look at multiple variables, an anomaly, for example, something when you mix fuel and air, right, a reacting mixture or a reacting kernel in that mixture can be represented as an anomaly where the chemical composition of this reacting mixture is different from the fuel and air, because you will not have the fuel and oxygen components, but now they are converted into intermediate species and products. The reacting mixture would initially be at a very low temperature. Now, after reactions, it will be at a very high temperature. So now the values are reaching, the variables are now having some extreme values in the joint distribution. That is how we want to characterize these anomalous events. And the second thing is these events would appear highly localized either in space or time. Okay, so if the event is happening everywhere simultaneously in the domain, we cannot label them as anomalous events. Only when you have these events occurring in a very small locality, we can pose them as anomaly detection problems. So now what we want to do is we want to use machine learning method, one that we have specifically developed in the recent past, to detect extreme events in scientific data. So now let me quickly recap how a simulation would perform, or what are the steps that are involved in a partial differential equation simulation. Initially, we start with some initialization. So this is typically done in terms of providing the initial conditions, specifying the grid size, looking at what are the turbulence models that you are going to use, all of those. Once we have these initial conditions, we generate the mesh in the geometry. Then we enter the time loop where we compute the right-hand side terms in our Garning equations. Then we use any of the ODE techniques like Runge-Kutta method or Euler's method to update the solution in time. Once we have the solution, we want to perform some analysis while the simulation is occurring. So we call this as in situ analysis. And periodically, we also want to save the data so that we can later analyze and understand the physics, right? So we also want to do some IO. And then this loop continues for about millions of steps. And then finally, you will end with the simulation. You end the simulation when you reach the end time. Okay. So now let's look at all of these steps. Here I'm showing you a picture of a 2D simulation of a diesel engine combustion. What you see here are these yellow regions where you have a flame or where you have a igniting mixture. So if you see, this region is very highly localized in space. So the reactions are happening only in a fraction of the volume or fraction of the area when compared to the entire domain. So now what we want to do in these green steps is to detect these and optimize the simulations to work only in these areas, right? That means the green boxes that you see in the workflow don't have to perform their operations in the entire domain, but they can be performed only in these yellow portions of the domain, which are only a fraction of the total size. So by this, if we identify this and deploy the computing only on these subregions, we can accelerate the reacting flow simulations. So that is hence the title that I have given, right? So now how do we identify? These yellow regions have a different chemical composition, different temperature that is significantly different from the background region, which is blue in color. So what we want to do is, just one second. Yeah. So what we want to do is we want to use machine learning techniques to detect these and optimize our simulation workflow. So we have done this successfully. I don't want to get into the details of this slide here, but what I want to mention is we have performed this on a climate data set, and we were able to achieve a reduction of 80% on the amount of data that you are saving from a simulation. Here, let me now introduce you the mathematical concept behind anomaly detection. This is a particular method that we have developed in our lab in 2018. So now to understand the mathematical aspect, let us look at the data that we generate. So let's say that I have performed a simulation where I measure two variables V1 and V2. So V1 is on the x-axis, V2 is on the y-axis. And I take these measurements and then plot them in this scatter plot. So you have a distribution of points that is given by this gray cloud of points. Okay. I label this data as normal data. And suddenly, let's say some ignition has happened, right? There will be some extreme points, right? So these points, these circles that are at in the bottom right corner, these correspond to the ignition kernel, okay? And these have extreme values. For example, if V1 is the temperature, right? The temperature is increasing, and then the fuel is getting consumed, you would have an ignition kernel that corresponds to this circular, this red circle. So now most of the domain or most of the region in our reactor is in the reactant stage. Only a few points are undergoing the reaction into the products, right? So now what we want to do is we want to identify the change in the distribution when compared to the left and the right images. In the left images, we have a single cloud of points that correspond to the reactants. On the right, you have some points that have moved from the main cloud of points to the bottom right. These correspond to the reacting ignition kernels. Okay. So now what we want to do is we want to come up with a method that would measure the change in distribution between the two data sets. So what we want to do is we want to characterize that data distribution. One of the popular techniques is in statistical learning, or this you also see in linear algebra, is the principal component analysis. What we do is we want to use PCA to identify the change in distribution. So in principal component analysis, we would have principal values and vectors. We want to see how the change in data distribution has affected the magnitude of the principal values or change the orientation of the principal vectors. I'll explain these in detail in the next slide. So let me briefly tell you what we have done here. In the principal component analysis, we have first scaled the data. Why do we scale the data? Because if you consider any major species, the mole fraction or mass fraction values will be really large. They will be of the order of 0.1, right, or 0.01. If you consider any minor species or intermediate species, they might have a concentration of the order of 10 to the power of -3 or 10 to the power of -4, right? So now you are considering this multivariate data, which have different orders of magnitude, right? Now what we want to do is we want to bring all of them to the same scale so that we will be able to get the patterns. If you don't bring them to the same scale, the variables that have really small values are insignificant, right? And they don't get any attention in the analysis. So first step is what we want to do is scale the data. Typically, we subtract the data by their mean and divide by the maximum value. Okay. Of course, there are other methods as well, where you can use a standardization process like in the normal distribution. The second one is step is to compute what is called the covariance matrix. Okay. The covariance is the variance in a multivariable setting. So standard variance is nothing but your standard deviation square, right? So you just compute the expectation of the random variable square. That gives you the second moment, right? But what we want to do here is in a multivariate setting, when we compute the variance, we get what is called the covariance matrix. So this is a variance between a variable by itself and a variable when compared to the other variables. So this is a measure of second order joint moment. So once we have the covariance matrix, what we do is an eigen decomposition to obtain the principal values and principal vectors. Okay, so now let me tell you what those are. So here on the left, I've taken the normal data set, which has a single cloud of points. We have done the eigen decomposition of the covariance matrix. And what we get are the principal vectors. Here we have considered two variables, V1 and V2. Accordingly, we get two principal vectors. The first one is a solid line, PV1. This is aligned along the direction where you have the maximum spread or the variance in the data. The second one is by construction. perpendicular to the first one. Okay, that is how you get these vectors for this covariance matrix in PCA, right? So what we are seeing here is the first vector is oriented along the direction where you see the maximum spread in the data. The second one by construction is perpendicular to the first one. So these are the orientations of the principal vectors. And at the bottom here, I have written the principal values. The principal values tell you on the weights are the contributions from each of these vectors towards the basis variables v1 and v2. Now we have performed the same analysis on the data set which has an anomalous event. This anomalous event, let's say, corresponds to a reacting mixture, right? So now what you see here is there is hardly any change in the orientation. The first principal vector still is oriented along the extreme or the maximum spread in the data. The effect of appearance of this anomalous cluster is very minimal or insignificant, right? Now, if you look at the principal values, the value of 0.21 has changed to 0.19, right? There is not much change in the principal values as well. So this is one of the standard machine learning techniques that is obtained, right, for dimensionality reduction or for identifying the distribution in the data or characterize the distribution in the data. So here what we observe is if you use any standard machine learning PCA, right, we are not able to detect the appearance of this extreme event. So the conclusion is that the second moment or the covariance matrix or the principal component analysis mainly captures the variance in the data. What we need is to look at the higher order moments. Okay, so and hence I will not get into the details, but I'll tell you what we have done here in a very brief manner. What we have looked at is a fourth order moment, which is a measure of kurtosis, right? Now what we have done is we have constructed a fourth moment tensor, which is called a cumulant tensor, and performed a decomposition of this tensor to get what we call as principal kurtosis values and vectors. Similar to the PCA, we have looked at higher order moment analogies of the principal component analysis. Now let's look at what happens. The red vectors are the ones that were obtained using the second moment or the principal component analysis, where we were saying that the reorientation of these vectors was not happening, or the vectors were not affected by the appearance of this extreme event. Now we have developed this new method based on fourth moment, and what we find is that the solid line, which would earlier be oriented like the second moment vector, is now reoriented itself to point to the appearance of this extreme event, right? So what I do is I randomly change the position of this extreme event cluster to some other location. So I moved this cluster to the location here. The second moment vector is still trying to capture the variance in the data. However, the new method that we developed based on the fourth moment has quickly reoriented itself to align with the extreme event, right? And again, we did the same thing. We moved the cluster, anomaly cluster, to some other location, right? It reoriented itself. So that means the fourth moment is very sensitive to any extreme change in the data, and it quickly reorients itself. And by looking at the orientation of these vectors, we can develop a machine learning technique or an anomaly detection technique to understand or to diagnose extreme events in our simulation data. So this is what we have done. So what we have done, we have applied this to a combustion data set, where on the x-axis here, I'm showing you the mass fraction of hydrogen. On the y-axis, I have temperature. Particularly, we are looking at what is called the syngas combustion here. Initially, our composition was uniform, so you don't see any variation along the x-axis in the points, in the circles that you see here. And we had some inhomogeneity in terms of temperature, so the points are distributed along the y direction. We have done the analysis, and these are the solid and the dashed line are the principal vectors. This is at time t equal to 0 microseconds. We have now started the reactions in our simulation, and we have now evolved to 4 microseconds. And what we see here is that the mass fraction of hydrogen has decreased for some of the points, and the temperature has gone up. Okay, so these are the points that correspond to an ignition kernel, and the vectors have reoriented themselves to track these ignition kernels. Again, I have to tell you that the values here are scaled. That's why you see negative mass fractions or negative temperatures, right? These are scaled by their minimum and mean and maximum. As we evolve the flow further, or as the chemistry in the reactor progresses further, if you look at 6 microseconds, more amount of fuel got consumed and the temperature has increased further. Accordingly, the vector, the solid line, has reoriented itself to capture these extreme events or the reacting kernels. Likewise, you go to a later time where all the amount of fuel, all the fuel component, the hydrogen atoms or molecules are consumed, and then now you are having the final oxidation of the system happening, where the mass fraction of hydrogen will now come down, and then you would see that the temperature keeps on increasing. This is again tracked very well in our analysis using this fourth moment, where the solid line, the first principal vector, quickly reorients itself to always track the ignition kernel. Okay. So in this, after this, right, this is a mathematical concept. Based on this orientation of these vectors, we have come up with some distance measures that will allow us to come up with a final number that will tell us whether there is an anomaly or not. That is done in terms of what we call as feature moment metrics. Here in this particular reactor, we had a total 12 chemical species, and we have also considered temperature. So we have in total 13 variables. To get the spatial locality, we divided the simulation into 4 different subdomains. And in total, we had around 20 time steps. What we have done now is project these principal vectors weighted by their principal values onto the basis. Okay, so this is nothing but a dot product of the principal vectors weighted by the principal values, right, which are these lambdas. And we get this single number that tells us how important a particular component among all these 13 variables is towards the occurrence of the ignition kernel. That is plotted in different graphs, which I don't have here, but I'll be happy to show towards the end if someone has a doubt. And looking at this metric F, we can now tell whether automatically whether ignition has happened or not, or which variables are responsible, or which chemical species are responsible for the ignitions in different stages. So that is a kind of detailed analysis that we can get out of this machine learning method. So here, this is a brief algorithm. I'll not touch upon this. So finally, I'll tell you what the result is, right? So we have performed a simulation of a 2D ignition process. The red ones are the ignition kernels that you see, and these occupy, you see, right, very small portions in the entire domain. Now, what we have done is we have put these white color grid lines to depict the spatial location of each of these. And then we deployed the machine learning algorithm or the anomaly detection algorithm. And what we find is that we find these 5 red spots in the, or 5 red squares in this entire domain. These correspond to the ignition kernel here, here, and here. So now what we have done is we have performed the simulation. Simultaneously, the machine learning method was also working to detect these simulations. And the method found that these are the locations where you have the ignition kernels. Hence, we are going to do further analysis or further data saves only from these regions, which are only 5 squares out of this entire large number of squares. That means we are going to reduce lot of amount of computing time as well as the memory storage by accelerating, and hence accelerating the simulations. So what is the accuracy of these predictions? It is provided in the last graph, where we look at true positives, true negatives, false positives, false negatives. You see that the false predictions are very small when compared to the true predictions. And this gives us the robustness of the algorithm that we have developed. So this is available as a reference in one of the journal papers that was published in 2019. Later, what we have done is we perform also simulations on GPUs. So we have accelerated this machine learning method on GPUs, where we got up to a 30x speedup. And why did we get this 30x speedup? This is mainly due to one of the key optimizations that we have done this is based on what is called a Khatri-Rao product. So these are so here Rao is Professor C.R. Rao, who is who was the director of Indian Statistical Institute. Khatri, I think, was his student. Both of them wrote a paper in 1960s. Okay, and that paper is called Khatri-Rao product. The expression for Khatri-Rao product is given here. It is an outer product of two different vectors or matrices, depending on how you are going to utilize. But that paper that was written in 1960s suddenly found its importance in current machine learning world, because same kind of operations happen when you do these tensor formations or these covariance matrix, any of those. So I would say that if someone is interested in exploring some old things, right, the legacy things, you can still find a lot of use of those things in the current machine learning world. For example, here we are able to speed up the code by 30%, sorry, 30x, which is a lot, right? Which is about 3000% faster when we run these things on GPUs. Finally, to summarize this part of the talk, where we have developed a machine learning method, what we have done is we have proposed an unsupervised anomaly detection method to detect ignition kernels and also tell us which variables or which radicals are important towards detection. We used both synthetic dataset as well as a dataset from an auto ignition reactor to demonstrate the working of this method. And this method in future, we are going to develop a scalable one for a massive DNS and evaluate its scalable performance as well. And we also want to extend this method to detect anomalies in other scientific phenomena like the crack propagation or weather datasets. Let me now move into the second aspect of machine learning, or where we can use machine learning in this scientific computing workflow. So here in this slide, I show you two images, the image on the left and image on the right. So the image on the left, as you see, is very blurred. You see broad features, right? So this is a beach where you have sand here, sky, water, and then some trees, right? But we don't see the leaves very clearly. We don't see the structure of these stem or anything clearly. So these are very low resolution images. But the advantage of these low resolution images is that they take very small amount of data size or data storage size. On the right, you see a very highly resolved image of the left picture. Here, in addition to the broad features like the ocean, sand and trees, we are also able to see the details of the stem or details of the leaves and so on. But to encode all of this information, this image size will be much, much larger than the low resolution image. Now, there are situations where sometimes storage is a constraint, right? For example, you have sensors mounted on these devices where the sensors have very small memory. In that case, we cannot store these high resolution images. We have to work with these low resolution images. But if you have low resolution image, can I actually make out what is exactly happening in the image? Right? That is the kind of question that we want to ask. So to put the same thing in a chemical engineering perspective, right? I want to run a simulation of a reactor. I don't want to run it on a supercomputer. I want to run it on my desktop, right? That means I cannot resolve all the scales in my flow. So what I will do is I'll resolve only the large scales in the flow, which is like the large eddy simulation or the runs. Performing the runs, can I now get a detailed information about the flow, right? So now these techniques where we give a low resolution image to a deep learning method and get this high resolution image are called super resolution techniques. So these are extensively used in our phones or in our if you use Facebook filters or Instagram filters, they are very widely used to enhance images, right? So now the question is, can we apply similar techniques to reacting flow systems, where we perform a cheaper, low resolution simulation because we cannot afford to run all the simulations on these high resolution supercomputers. But we want to get the quality of the solution to be very similar to this high resolution. So that means, can we come up with super resolution networks for flow physics that can take LES or RAN simulation and give us a DNS-like quality flow fields. So that is also here again I'm showing a second picture. Again here you have a degraded low resolution image, right? And on the right side you have a high resolution image. Okay, so there is a question in the chat from Shweta Chauhan. So the question is, what is the use of neural network in chemical engineering? So I would say that there are several applications. I list about 3 or 4 applications. So for example, you are doing a reactor modeling, right? So now in this reactor modeling, you might convert some chemical A to chemical B to C, and there are a chain of these reactions, right? And now if you want to keep track of all of these things, it might be very difficult. And especially in the cases where there is uncertainty. For example, let me give you a simple scenario. You have petrol, right? Petrol comes from different, you take petrol from Indian Oil, right? And petrol from Bharat Petroleum. The broad composition might be the same, but if you look at the details, there might be slight variations in the quality of the petrol. Again, we consider the same company, right? With respect to different batch numbers of Indian Oil, the composition of the petrol might change slightly. So in all of these cases, right, you want to use a modeling method, a neural network, to estimate, irrespective of different compositional changes that are perturbed about some mean value, how will be the efficiency of the engine. Can I do a modeling of that, right? One way to model is to perform all of the simulations and then tell you what the output is. The second way is, once you have generated all of the simulation data, use that simulation data to train your neural network, saying that, okay, if this was my chemical composition of the petrol, this is the composition, the output has varied by this much. To train this, in future, when you extract when you get a new set of batch of petrol from the refinery, now you can predict, right? Okay, this is the quality of your fuel, the combustion is going to happen like this, the efficiency is going to be this. So that kind of input-output mapping can be done using neural networks. The other examples. Hello. Yes.
Yes.
Did I answer the question?
Yes, sir.
Okay. So now let me proceed further. I'll give you similar examples here. All right. So here I'm giving you an example of a deep learning method where LR is a low resolution image, HR is a high resolution image, which is on the right side. So this is our input, this is our output. Of course, you can use any interpolation technique to get this low resolution into ILR, what we call as interpolated low resolution image. A plain interpolation will not give you high resolution. It will not give you all the spine detail features. So what we do is we pass them through different layers of these deep learning network. The layers have these 3 different functionalities. One is called patch extraction, where you pass them through a convolutional layer that will extract different smaller features in this entire image. Then you do a nonlinear mapping between these features and the latent space. And then once you have this latent space, you extract the features and then reconstruct the image using in a high resolution manner. Okay, so this is the architecture that we have, and these are called SRCNNs, super resolution convolution neural networks. So again, just to summarize here, what we have done is we have taken a low resolution image and then feed that through a network, and the network will provide us the high resolution image with additional small scale features that are embedded that are missing in the lower resolution image. So how do we apply this technique in our flow simulation? So here I'm showing you a direct numerical simulation of the flow in a channel or like a pipe. If you see this, the flow has a lot of these fine scale structures, especially near the walls. These dark blue to green transition, you see a lot of small structures. if you perform a low resolution simulation, a cheap simulation like LES or RANS, what you would find is these fine structures that you see here are not present anymore. You will see these pixelated kind of images, right? So this is what would have. So here now you see that the broad features are still there, where the yellow is around the center line. You see these wall structures, but they are really coarse, right? So here what you have done is we have taken an image or simulation that was performed on a 512 square grid. We have degraded that like an LES simulation into a 64 square grid. So all the fine structures in the simulation are gone. Now the question is, can we come up with a network where we give this as the input, this low resolution image as an input, and get the high resolution, right? So we are giving the low resolution as an input to our network. We call this as a flow network, and reconstruct the flow field at high resolution. And can we get that high resolution image similar to our direct numerical simulation? So this is what we want to do. So here we consider the same networks as I have shown earlier. So here we input these flow images and we get these high resolution images, right? There are again two techniques. The first one is based on convolutional neural networks. The second one is based on GANs or SR GANs to be precise, super resolution generative adversarial networks. Here again, you provide the low resolution image and you have the high resolution image. So now the question is, can we use standard imaging techniques, right? Standard networks in the case of fluid flows or in the case of scientific data? The answer is yes. But in this case, when you use any normal image analysis methods here, what would happen is the high resolution image will have more structure, but it may be physically inconsistent. That means the data that you have generated from the network may not obey the laws of physics, right? So that means it may violate conservation of mass, it might violate conservation of momentum, right? That cannot happen. So that means now you have to come up with these physics informed neural networks, often referred to as pins, where any of the constraints that we have, for example, like the conservation of mass or conservation of momentum, you code them up in terms of some loss function. That is what is depicted here, right? And then now your network is interpolating the data from low resolution to high resolution such that the loss function is minimized. That means you are going to obey the conservation laws. So these are the kind of things that we are looking at. So what is the advantage of these things? So if we employ these kind of techniques along with our simulations, we can significantly reduce the computation time and we can perform accurate simulation of industry designs, right? So for example, if I want to design a reactor, right, and there are several parameters for designing a reactor, how do we optimize the parameters? Obviously, we cannot do detailed simulations. What we can do is we can use these networks to give all these parameters, and the network will give all the outputs, and from that you will choose the optimal set of parameters. So this will accelerate the optimization workflow. Then again, the key important thing, as I was saying in the last slide, is it needs to obey all the physical laws or constraints, like the temperature cannot go negative, right? The density cannot go negative, the mass fractions or mole fractions cannot go negative. Those are the kind of constraints that we want to impose when we do these network operations. And then finally implement these laws into the loss functions. So that is what we have done. And here is an example of one of the network predictions that we have done. So this is the input image that we have provided to a network that we have generated. And if you do simple bicubic interpolation, it gives you an image like this. We have looked at different kinds of neural networks and then quantified their performance when compared to the ground truth that is given here. So what we have found is that SRCNN, super resolution convolutional neural networks, where we have informed the losses based on physics constraints, has done the best prediction when compared to the ground truth. So again, if you consider the same pipe flow or the channel flow, Here is a ground truth. If you do a simple ground truth or the high resolution image, if you do a simple bicubic interpolation, you get this kind of a blurry image. But when you pass it to a super resolution network, right, you get this image. Of course, it is not close to the DNS simulation, but it is much better than the simply interpolated image. Right. So finally, I want to give you a slide about perspectives on where we can use machine learning in different aspects. Right. The first thing is I have a reaction system that has about 100 chemical species. Right. But I want to identify 10 species that are key to my reactions. How can I do that? So you can use dimensionality reduction techniques or principal component analysis to obtain what are those 10 important species. Right. And again, I have this a lot of chemical species, but I don't know their properties. What is their mass diffusivity? I don't know what the viscosity of the mixture is. How can I get those? Earlier, we had to do all of these experiments and then measure those and do it. But what we can do is we can train the networks to predict these kind of properties. That is one more application. In terms of flows, right? When you perform LES or RANS flow simulation, we can use super resolution networks to model the subnet or the Reynolds average terms or Reynolds stress terms. The second thing is again to perform intelligent simulations where we can accelerate using either anomaly detection or using super resolution networks, the simulation by reducing the simulation time and increasing the efficiency of the simulation. And again, these kind of works are extensively being pursued by many of these popular companies. I'm sure that many of you have used ANSYS or Converge of any of these solvers, right, for your process modeling. And they are investing a lot of money in putting in these methods into their software packages. In terms of industries, right, my lab, we are actively collaborating with Shell and Siemens to incorporate some of these ideas in their process development. Okay. Right. So with this, I would like to conclude. So here I have provided you a brief background on scientific computing. I have highlighted the importance of turbulent flow simulations that are done on really large supercomputers. And I have shown you two methods, right, where machine learning is being used. First is anomaly detection method. The second is super resolution networks. So with this, I've given you a brief idea about how ML AI can accelerate the simulations of reacting flows. With this, I'll be stopping my lecture here and I'll be happy to take some questions. Thank you.
Thank you, sir. Now session is open. Participants, you can ask questions. You can ask in chat box or you can raise your hand. Sir, for simulation, which software you are using?
So here we don't use any of the commercial software. We write our own software because the commercial software are still not yet capable of doing these high resolution simulations. So we develop our own code based on our own numerical methods, right?
Okay.
Or the numerical methods that are part of our standard textbooks, and develop this specifically for these applications.
Thank you. Any questions? I think.
Okay, so there is a question from Augusta. Basic software knowledge we need to do the simulation. So I would answer this in three parts. Okay, the first part is where you are going to write your own code. Right. In this case, you would want to know C, C++, or at least Python, MATLAB. Right, and then you have to know the numerical method that you are going to use for solving the governing equations. So, for example, again, so you want to do this only where you want to learn the basics on how these array solvers are developed. But if you are interested in solving a problem of interest, there are two options. There are several open source codes, right? For example, if you want to do a simple 0D or batch reactor or Wellster reactor or PSR, there is something called Cantera, which is a Python package that you can just Google download it from their website and use and perform these reactor simulations. They have different kinds of reactor setups that are available. I think usually people in combustion, the commercial one is called Chemkin, right? That is developed by ANSYS. But if you want to look at the open source version, you can look at Cantera, which is really good for either combustion or as well as if you are looking at surface chemistry reactions and so on, like catalysis. Then if you want to perform a device level simulations, I would suggest again, there are two things, right? Commercial and open source. In terms of open source, for the flow simulations, you have what is called OpenFOAM. It has a lot of training material that is available on websites, and there are a lot of training videos available on YouTube. And also they conduct a lot of webinars to train different people, train different aspects of OpenFOAM. This is a software that is written in C++. It runs on a standard computer like laptop or desktop and can also work on big machines like a cluster or a server. The commercial equivalent of these are Fluent, ANSYS, right, or this Star CCM, any of these softwares. Again, of course, here you have to pay. What you would receive is more sophisticated user interface, right, and also better support in terms of if you have any issues. So they have commercial options as well as the uh, open source options.
So there is a need of knowledge of C and C++ language for machine learning and data science.
For machine learning and data science, I would suggest that you better work with Python than C++. Right? Most of these things can be done using something called PyTorch, TensorFlow, where you can call these packages in Python and then develop your networks, create a training model, do the validation and inference. So if you are interested more on the machine learning side, I would suggest that you learn Python. If you're more interested in the computing side, then I would suggest you learn C++.
Okay. One more question is there, sir.
Yeah, how to couple deep learning with software, commercial software like ANSYS. Okay, so I think commercial software will let you use what are called these UDFs, user-defined functions, right? You can couple your deep learning method through these UDFs. But I know that ANSYS is working on incorporating these deep learning techniques in their solver itself, right? I spoke to them about a year ago, where ANSYS is investing a lot of resources on putting these deep learning techniques into their solver itself. So maybe in future releases, right, they will have ways that can couple both seamlessly. Right, we don't have to put in the code, but they will have the code. You just tell them what options you have to use, like currently the way you use them for the solvers.
Okay. Thank you, sir. And thank you for your resourceful speech. This informative speech is going to be more productive for the diverse group of participants in this FDP platform. As the content of the scientific computing has been elaborated in a beautiful way, that the clear understanding have been created among each of us. Professor gave detailed note on turbulent flow simulation and brief introduction on parallel computing and explained some issues and possible solution for the Excel computing. Sir gave detailed note on various applications like hypersonic vehicles and in energy sectors. Professor elaborated about machine learning techniques with very informative and give very good examples of deep learning. So for this, thank you so much, sir. Thank
It's my
you
pleasure. Thank
for
you.
accepting our.
Thank you.
Thank you from the Department of Chemical Engineering, as well as from the management of MVG College of Engineering. Thank you so much, sir.
Yeah, thank you. My pleasure. So can I disconnect myself?
Yes, sir. Yes, sir.
Yeah, thank you.
Participants, feedback form is there in chat box. You can fill. And the next session will start tomorrow at morning 9 o'clock from Mr. Dr. Anand Govindrajan, Assistant Professor, Department of Chemical Engineering, ISC Bangalore. Okay. Thank you all.